This conference will now be recorded.
Sure. So you're asking a question, basically you are getting null pointer exception most of the time. So what is the way you can get it sorted?
Yeah.
In a deterministic way or a faster way, right?
Yeah.
Okay. So reason behind null pointer exception is anytime if you have like LL node H, if you have it null and you are trying to dereference that either dot data or dot next, right?
Yeah.
Yeah. So guideline I'll give you is whenever you are trying to access H dot data, just look at the code above it. Have you made
Okay.
sure that H is validated to be not null? If I
Okay.
give an example to you, print linked list. Okay. So I say LL node H. Now I say while H dot next is not equal to null, H is equal to H dot next. And I also do printing of the data of that node. So this is what I do: system dot out dot printf H dot data, right?
Okay.
Now let's analyze the code line by line and see what we are trying to do. Here I am trying to do H dot next.
Yeah.
Correct? Question that I should be asking myself is, hey, before this, did I validate whether H is null or not? Because this line will throw null pointer exception if H is null, correct?
Okay. Yes.
So what can we do so that we are not causing this problem here?
We can actually handle the case where H equal to null.
So we can say if H is null, print linked list based on the question, what we want to do. Like here, let's say we are returning.
Yeah.
Right? Now, this is safeguarded when entering. Now, inside the loop, we are trying to print H dot data.
Yeah.
Can we say here H is validated to be not null?
Yes.
Yes, because we validated it before this, but that was just before entering the loop. Inside the loop also H is changing. Can you think of any case where this code that I have written will throw null pointer exception? Can you give me a list example where this will throw a null pointer exception? Think of this, Prakash. Can this make H null?
No.
Why?
Because it won't enter the loop if the H dot next is null, and therefore the 17th line won't cause H to be null.
That is for first node only, Prakash. Think of little bigger linked list and tell me. What will this code do for linked list 1, 2? Think about it. What will this code do? Oh, yeah, this will not cause it to be null because we are breaking beforehand. Yeah. Yeah, Prakash. So we will not do that. But now can this do null pointer exception? So, okay, let me just see. Maybe it's a wrong example. Initially, H is here.
Yeah.
We go inside, we modify H to 2 and we print that. And then when we go up, okay, it will become null. Yeah, in this case, we will not cause it. So ideally, when we are changing H, we should be cautious that when we are changing, is it becoming null? Are we entering the loop with null again? So that is the guideline that you are asking for, is this, that before trying to use H dot data, H dot next, you have to make sure that H will never be null. So a perfect example of that was print alternate nodes. Reason this question was given is that only.
Okay.
Because with even odd length linked list, we will hit that case sooner. Because if you are printing alternate, if you say print this and make H is equal to H next, you reach null. Here also you print 1, h is equal to h next, you reach 3. So in this case, chances are that we will land up to a null node. If we do not have a check in place, we will hit null pointer exception. Make sense, Prakash?
Yes. So as you just mentioned that we have to check that h dot next condition. So in that nth node from the end problem, let's say we are given k, and we are moving forward the first pointer k nodes ahead, and then we are starting the second pointer, and then we are traversing to the end, and
Right.
the second pointer would be the our answer, right? So in that
Mhm.
case, we will have to check for the base case, right? That whether the linked list already has k nodes or not.
Yes.
So how do we do that? Because it is given that we need to do it only in one loop.
Yeah. So if I say give me fifth node from the end, how many steps you are moving fast pointer?
Uh, 5 nodes, 5 steps
Yeah.
first.
So we are actually going and moving it 5 times, right?
Yeah.
For int I is equal to 1 I less than equal to 5 I plus plus, you say f is equal to f dot next. This is another good example. Now think about it. What will happen to f if this is your linked list? What will happen in this loop?
A null pointer will be thrown.
Exactly. So what you can do is you can say if before that, if I say if f becomes,
Okay, got it.
so this is again, now you see what we are doing is before doing f dot next, we have brought in a check that f should not be null, because we know if it is null, this right side that we are trying to do will cause a problem.
Yes.
So this is safeguarding that we need to do for every access to next or data that we are doing.
Okay. Thank you.
Most welcome.
This conference will now be recorded.
Okay, let's start. So far we have not touched matrices. There are a lot of questions on matrices also. Now is the time where we are going to talk about. So what all should we know about matrices? We're talking about two-dimensional arrays or matrices. So the language that you code in, you should be clear on how to declare a matrix. So people who code in Java, they are clear how to declare and instantiate a matrix. So what is the Java syntax? If I want to declare and create a matrix of, let's say 4 by 7, 4 rows, 7 columns, if I want to create a matrix, what is the syntax in Java? Int
And square bracket,
matrix
matrix equal to new int 47.
int 4 7.
7.
Yeah, so this is the way we do it in Java. C sharp way has a comma. C sharp way goes like this, is equal to new 4 comma 7. Little different syntax, but that is C sharp syntax. If you want in C++, again similar to arrays, we say 4 and we say 7. So we should know how we declare an array or declare a matrix in the language that we code. That's important thing. Second important thing is how do we pass matrix to a function? In C++, we'll stick to a notation. Right now I'm just writing print matrix. So if we are passing a matrix to a function, we write m, and what we will do, we will end up giving max row, max column. We will give both the dimensions. Ideally one is optional, but we will stick to using both. What we will do, based on the problem constraints, we will define a global variable called max row, max columns. This is like hash define, and whenever we are creating the matrix, we will create the matrix like max r, max c. This will help us avoid some of the mistakes while passing the matrices to the function. And r and c will be the actual number of rows and columns. So this is what syntax we will use in C++, all the programs. We will make either hash define or you can make two constants which are global. This is the capacity. It is not necessary that we are using entire size, but we are declaring with that size. And R and C, typically problem statement gives us number of rows and columns. We read that and we fill a matrix. So this is passing. So this is C++ way. Now what is Java way of passing to the function? If you are writing a function in Java, print matrix. How do we receive a matrix?
Just the name of the matrix is enough, I guess.
Name of the matrix is enough. Now the question comes, how do we know from name of the matrix how many rows it has, how many columns it has? You want to
Rows
know?
would be mat.length and columns would be mat0.length.
Yeah. So mat.length is number of rows and column is, we believe like every row in the matrix is of equal length, and this will give us the column. So this is the basic thing that we should be aware of. 2D matrix can also be seen as array of multiple arrays. Can we say that? Can I say these are 4 arrays, single dimensional arrays? If I call it, this is M0, this is M1, this is M2, this is M3. Then we say this is like a matrix of 4 rows and columns wise depends on, let's say, if we have 3 columns. So ideally, if we try to access M0, we can deal it as if it's a single dimensional array. If you want to do a binary search on this, we can do it on M0, considering M0 is single dimensional. So this is to be aware of for matrices. How do we declare and instantiate them? How do we pass them to a function? And reason we are introducing this is because the concepts that we have learned so far, many a times there are questions of those concepts that come on two-dimensional matrices. One such example, if we take, let's say I'm drawing a two-dimensional matrix here, 2, 3, 5, 9, 7, 0, 4, 1, 8. The problem statement is, given this matrix, start from this element and stop at this. This is our starting point. This is our ending point. And problem statement says print all the paths that are possible from starting point to ending point, and you are allowed to move in 2 directions. You can move right from any cell or you can move down. So what are the possible paths that we are seeing? Can you speak the numbers that we path?
23508.
23508 is one path that we are seeing. And what is
23708.
it next?
23708.
3708, yes.
29718.
2, can I say 23718?
Yes.
Same way you are saying 2, from 2 3 we are done with all the paths. Can we say that, or there is one remaining? We are done with all the paths starting from 2 and going through 3. Then 29708, 29718, 29418. That's it. This is a path printing problem, and we have done similar problems not on the matrices but in the, we have done path printing problems in backtracking. Wherever we see the tree structure, sometimes tree is explicitly given and sometimes we have to visualize the tree, right? Now same problem, if I ask you go and code on a matrix that given this, will you be able to do that? Yes. The difference is, in tree we used to go left and right. In n-ary tree we used to go to all the children because those used to be the options. Here when you are going left, if you are at if you are at I and j, when you are going right, what is changing in ij? J is changing because you are going to the next column to the right, so j is increasing by 1. When you are coming down, I is changing. So it's I plus 1, right? So if we can keep track of I and j, and we can keep track of boundaries, because in tree, tracking boundaries was easy. Because if any node does not have a left, that used to be our base case. If left is not there, return. If right is not there, return. Correct? Here, the boundaries will be the dimensions of the matrix. Total number of rows, total number of columns. Right? So this problem, we can at least visualize how we will go about it. Right? Okay. Now, today's focus is not path printing problems. Today's focus is, there are two more categories of problems that we will talk about in backtracking, which is one, Boolean answer problem, and second, we will say this is integral answer problems. Usually these are count kind of problems, min or max. Right? So let's see what we are talking about here. And this is where we can optimize our backtracking better. In backtracking, if we are printing the paths here, can you tell how many paths are possible in a matrix of size m cross n? Huh? M plus n. Okay, this is on top, m plus n, and you're saying it's like NCR formula. That's what you're saying. Will it be that? Okay. So now you're changing the formula. But this is the problem we will solve programmatically now. Right? So we are saying we want to count this path. You can validate the formula that you came up with. But we want to count how many paths a matrix has when its dimensions are given. And the paths, criteria for the path is it starts at 0, 0, ends at the index of the last cell. No, not mn. M minus 1, minus 1. If the dimensions are m cross n. So let's see what we want to do here. We want to count the paths which are starting from 0, 0, ending at the last cell. And what we will try to visualize, or what we will try to do is, we will try to define this problem in terms of states. And then we will see the relation between them. So what we are doing is, we are going to recursively define the problem, and we want to calculate. Right? So if we have to define the problems recursively, the most important thing is to come with the size estimates, or come with the index estimate. That is where we used to say this is our helper function, right? So normally if I ask you what will be the function signature, if I say given a matrix of some dimension, you have to give what is the total number of paths starting from the top left corner to bottom right corner. So can you come up with a function signature and tell this is what it will take, this is what it will return. It will return int because we are looking for number of paths. Okay. Yeah, what will it take? Count paths from 0, 0 to bottom right cell. Okay, rather than 0, 0, I'll call it origin to bottom right cell in a matrix of given size. Yeah, return type is clear. Function name, count paths, input parameters, matrix, and no, we want the original function so that we can formulate it according to the problem statement. Do you really think matrix is needed here? For total number of paths, do we really need matrix? Is it dependent on the values in the matrix?
No.
Ideally, it is not. I can get rid of this, right? Because given R and C, we want to tell how many paths are there. But sometimes this problem also gets twisted. What they say, the matrix is given. Wherever there is a 0, like we see 0 is here, they say you cannot go through that cell. It's a blocker, it's a wall. Then paths will certainly reduce. Those are the next category of problem where we try to, like we did in backtracking, one was print all the paths, and second we have done print selective paths where we have to put if else, like generate all the balanced parentheses, generate all the binary patterns of n bits which have a bit set. Those were conditional, right? So let's take a look at this. First, we are not taking matrix. This is your initial thing that you want to calculate. Can you convert this in terms of size? Think about the recursive calls, how you will utilize the recursive call. Spare some time, think yourself, and then we will do a discussion. But what we want to do is we certainly want to go recursive way. And one more thing I missed. From any cell, we can go right or down. So this is the problem statement. Give it a thought.
This conference will now be recorded.
Yeah. Any thoughts, any ideas? Problem statement is clear to everyone, right? Given any matrix of any size, here we have given it as 3 cross 3. We want to know how many paths are there from this place to this place. Okay. Okay.
Suppose the RNC exceeding the limit,
Right.
we have to add the other. Like first R should be 0.
Correct.
Then C should be increasing.
Okay.
If C is exceeding, then R should be increasing number.
Okay. So this function that we are calling initially, I'll call it with 3 3. Those are the parameters I'm passing you, and you have to tell the count. In order to solve the problem, if you require some other indices, helper function, you can do that. Yeah, Rajesh. Huh? Yes. So first important observation is in this matrix, if I want to know paths from S to E, I have two choices. I can ask a question to S. What is the question we will ask S, that index? Give me count of paths that start from U and end at E. Correct? Can I ask a question to E also? One way is I ask that question to S. S somehow calculates recursively and gives the answer. That's one way, coming from upper to this side. Second, if I ask the question to E, hey E, from U, give me the count of paths that start from U and end at S. Both will be same. So we can start from either direction. Rajesh, you were saying something? Same thing. Okay. So in both the cases, we will try to define the way we want to think recursively. So Rajesh, which side you are going ahead from, the back side or front side? From the start. So if you are coming from start, you want to ask a question at ij. So the way we formulate this is, we are asking count of paths from I and j. This we want to somehow define, correct? Initially our I and j, if we are starting from the start, will be 0 0. In order for this guy to tell the answer, he has to find the answers from its neighbors, right? So who will he ask? His right neighbor, which is 3, and down neighbor, which is 9. Let's say right neighbor gives him the answer. When we think recursive, when we say we are asking recursively, we trust it will give the right answer. Right? So we do not go inside how it is calculating. So 0 0 asked the right guy, it gave the answer. It asked the down guy that gave the answer, what will this do with both these answers? Add them. Is that sure? Is everyone saying that we will add whatever answer comes from right and whatever comes from down? Yeah, because when we start from the right, some paths will start with 2, 3, right? All the paths starting with 2, 3, if we can get the count of that, and all the paths starting with 2, 9, if we can get the count of that, total paths from 2 to 8 will be sum of those. Everyone agrees? Right? It is sum of these two. So we have defined, when we are saying sum, we have also defined when they give us an answer back, what will we do with the answer, right? So same thing, can you help me write in terms of a formula? Count paths from ij to end, what will it be equal to? Yeah, it will be sum of two values. What are those two values?
Count paths I plus 1j
This is total paths from ij to, yeah,
I plus 1j
count
plus
paths of,
ij plus 1.
think about it, what we are saying. We are coming from top, so we have to ask the right and down.
Count
I
paths I plus 1j
plus I plus 1. Everyone agrees with this? We are asking right neighbor, we are asking down neighbor. We have defined the recursion here. Huh? Boundary case you are talking? Yeah. Boundary and base we will write separate. Recursion when we write, we do not worry about boundary and base. Now let's talk about base case. Base case is, what are the values of I and j who will be able to confidently return an answer and who do not have to ask recursively? When I is equal to r minus 1, j is equal to c minus 1, then we say your answer is, how many paths are there from last element to last element? Only one path? That's the same element, right? So count of r minus 1, c minus 1 is equal to 1. And we were talking about boundary also. So we say count paths of I, j is equal to, what will be the count of paths if I and j are greater than, if I is greater than equal to r or j is greater than equal to c? Can we say that? If we ask in this matrix, start from this cell and give me paths from this cell to last cell, 0. This cell is not there in the matrix, right? So that becomes our boundary case, right? This is our recursion when we were saying top origin to bottom cell, right, to top left. Whatever we discussed with Hart, can you write recurrence relation in the reverse direction also? So spare some time, write all these three things. Base, boundary case, for if you were coming from the back side. Right now we started, we were asking the question to 0, 0 and said you give the answer. So 0, 0 said, to give the answer I will ask right and down. If you are asking from the last cell, this cell, you give us the answer. Who will this guy ask? Upper and left. So just go and define this so that we do this exercise from both the sides.
We can do count paths RC equal to.
When we are writing count of path of ij, this is very important how we are interpreting it. Here the interpretation was starting from u, ending at r minus 1 c minus.
This conference will now be recorded.
So you're talking about when we are at 5, we cannot go right. When we are at 8, 8 is the last cell. Yeah, if you are going from 8 to 2, that 8 is asking upper guy and left guy. It is going left and up, yes. One way we talked about solving it. This is one way we talked about solving it. If we are coming from top, this is how we will come up with recursion. So we are saying, if we were coming from backside, what will be your answer? How will you write recursion differently? So that is what we are thinking and doing. Yeah, anyone?
Here we will take row length and column length.
Yeah. So Ravi, what is your answer? You're saying count paths.
Count paths of row column -1.
Row column -1. We are
Uh,
defining I and j count paths.
yeah, I am taking I as row and j as column.
Sure. Should be equal to what?
Count paths of row column I j -1
I
j
j
-1
-1. This will be
plus
which neighbor?
this is left one in
Left
this
neighbor.
case. Yeah,
Okay. Plus.
count of I -1 j
This is upper neighbor, right?
upper. Yeah,
Everyone agrees. If you are coming from downside, this will be the way we write recursion. Okay. And what is your base case, Ravi?
uh, base
0 0 equal to 1.
yeah.
If you are asking 0 0, you tell me path from u to 0 0. Then 0 0 will say there is only one path, no more. Right? What will be the boundary here? Count of ij is 0 if I less
I
than
less than
0
equal to and j less than
and
0.
or.
Or
Right? So we are able to visualize recursion. Right? Now we can use
and
any of these approaches to solve the problem. Right?
Sandeep, earlier you
Yeah.
said that this is a backtracking problem, and now we are saying that recursion we are alternatively using the terms for the same thing. So just a question, how would backtracking differ from recursion if we were to say that it is actually different?
Sure. So can somebody help me answer the question that Prakash has? Prakash said that earlier we were saying this is backtracking problem. Now we are going recursion. So what is the relationship between recursion and backtracking? More than one option. In backtracking, at every stage we have more than one choice. So do you see, Prakash, we are making two recursive calls, one here and one here. It's just that we
Yeah,
wrote it mathematically. But when you write in terms of this function, ideally this will be calling this function
yeah,
with two values. Ideally, right now the way function is written, it has only R and C. So we can go with only bottom to top approach. But if we want to convert this into top to bottom approach, then we will write a helper function with two more indices I and j. We will first pass 0 0 to it. Correct? So Prakash, since we are making two recursive calls, that's where it becomes backtracking. Backtracking is also recursive, but it is where we have more than one choices at any stage. Does that make sense?
yes,
Okay. So now, if you see, once we have come to this stage, writing code for this is no big deal, right? We just have to convert, translate into code, correct? One more important thing to analyze here. Here we are counting paths. We don't have to print the path. Another approach somebody could have said is, let's generate all the paths, and at the time where we were printing the path, let's do a global variable plus plus. That way we will count also, right? But in this, we do not have to generate paths. So why go that step? So what we try to analyze now is we see this problem and we try to see what calls we are making and how we are proceeding for this problem. So initially, at this, initially we make a call to 0 0. Let's say we are going from top left to bottom right. What two calls does it make?
0 1 and 1 0.
1 0 and 0 1. What two calls does it make? 2 0 and 1 1. What two calls does it make?
30
3 0 and 1.
2.
Right? But 3 0 is the case that we talked about, a boundary case. If I becomes greater than equal to r, we will return from here. So 3 0 will not make further recursive because this that we have hit, this is our boundary case. But 2 1 will continue, right? Where will 2 1 go? It will make a left call to 2 2 and right call to, the left call will be to 3 1. 3 1 is again a boundary case. We do not go beyond that. 2 2 is our base case in this case because This is r minus 1, c minus 1. This base case will return 1. Let's continue with 1, 1. What calls will 1, 1 make?
2 1 and 1 2.
1, 2. Okay, what calls will 2, 1 make? 2, 1 is a boundary case.
3 1
3, 1
and 2 2.
we saw something similar here.
We can
Right?
use DP there.
1, 2 will make 2 calls. 2, 2 and 1, 3. 1, 3 will hit a boundary case. 0, 1 will make a call as 1, 1 and 0, 2. 1, 1 we have solved earlier. So what are we witnessing here?
Repetition of
Witnessing
steps.
DP. And the way we reach DP is we tried seeing, this is the state transition we are doing. Whatever variables are changing, we just try to draw a tree and see, are there any calls which are having same parameters, and we are doing calculation again and again. This is something similar we saw in Fibonacci, right? This is something similar with 3 problems that we did: Fibonacci, NCR we were calculating. We saw that somewhere sub problems were recurring, and this is the perfect example where we say we can apply dynamic programming. Now we learned 2 types of dynamic programming. One we said was
Down
in DP there are 2 ways of solving: top down
and bottom up.
and bottom up. Top down, what does it say? Yeah, when you calculate a value, remember them. Next time you make a call with the same values, reuse them. So we used to write a recursive function, then take a DP. In this case, the DP will be, since in your state 2 variables are changing, you will take a 2-dimensional array, fill with all minus ones. Whenever you calculate an answer, remember that answer. If it is minus 1, calculate. If it is not minus 1, reuse. That all everyone remembers we talked about. So that's the way. Just now we thought recursive way. This recursion we can convert into top-down DP easily. All that we already know, right? But now what we will see is, once we have come up with recursive formula and base cases, we don't have to go with top-down approach, because we saw top-down approach had a flaw that it uses recursion call stack, right? Let's try to follow the bottom-up way. The bottom-up way says, start with the base case and start filling your matrix. That's the bottom-up approach, right? So let's take a bottom-up approach for the same matrix that we saw. So far we have identified it's a 2D DP problem. That is clear to everyone, because 2 variables are changing in recursive calls. That tells the dimension of DP. Now let's say we take another matrix which we call as DP matrix. We want to fill that completely with the solution. So this is the solution matrix we are taking. We can start from this or we can start from this. Where do you want me to start from? From S. So if we are starting from S, we want to know that answer. When we started from top, our recurrence came was, this is the recurrence that we came up with, right? I put that here. Let me move it here. Yeah. We are starting from the top. This was top to bottom. No? This is bottom to top. So we have taken it correctly. Now in this, what is our base case? 0, 0 is our base case. So let's say we want to fill that. No, base case was r minus 1, c minus 1. Oh, wait, did I write it reverse way? So this is correct only, na? In top to bottom, this guy knows his answer confidently. He doesn't have to find recursively. Correct? So our base case was this only. So his answer we already know is, pen has stopped working. Now it will be fine. Yeah. So can I say this answer I know confidently? This is 1. We are saying from here to here, who knows the answer? Let's start filling from the base case side. From here to end, what is the answer?
Plus
He
1.
doesn't have any right neighbor, he has only down neighbor. So if you are in the last column, can we fill the last column straight away? This is 2, this is. Can we fill last row straight away? Paths from here are 2, from here are no 1 1, sorry, because they do not have the other neighbor. So other side will give 0. There is only one path. So this is 1 1. So when we are going bottom up, can we say last row and last column can we fill straight away? 1 1 1 1 1 1. Now what is the answer here? 2. This answer is this value and this value. This is pre-calculated now. What will be this answer? Add this value and this value.
3.
3. What is this answer?
3.
What will be this answer?
6.
6. This is our answer. Right. So now if you see, it is just a 2D matrix filling problem. Go and fill the 2D matrix. That's the path that we are counting. This will be our final answer. Correct? And if you are going from the other direction, base case was this. If we say, like we are asking this question to this cell, you give the answer. If he has to give the answer, he has to find recursively. So we start with the base case. From this cell to this cell path is 1. Here also it is 1. Here also it is 1. So you fill this row and this column straight away. And then all remaining we start filling based on the previous two values. Correct? This is called bottom up DP. We just take a 2D matrix, we start filling and we are done. Clear? Yeah. Where should be 0? Previous that we traced. Here. No, we are starting here and reaching here. That's right. No. What each cell is representing for you, it's very important to keep in mind. Each cell is storing the value, how many paths are there from U to end. Each cell is telling you that. There is one path. Yeah. So you can reach from end to end. You can be sitting there. There is only one way to reach. That's you are sitting. Can I say like you reached 8 to 8? That is the path. If you are already there, that also we treat as a path. We cannot say 0. If you are sitting at the end, you have already reached the destination. There is one way by taking 0 steps. Right?
So in the case in this case with bottom up DP,
Yeah,
we don't actually need recursion with of any kind, right?
absolutely. We get rid of recursion completely. Right?
Okay.
That's the beauty of bottom up. Is it clear? Okay. So this was one way to kind of help you visualize how do we solve a problem when it is a backtracking problem. On 2D matrix, it becomes easy. Similar problem I can also give you on tree. I can say in a tree, how many root to leaf paths are there? Count and tell me. Root to leaf paths in a binary tree. You will be given just root. The answer you will return will be on tree. You will say int count paths root. Now, can we visualize recursion here? What will be our answer? How will we return count of paths from root to leaf?
First we will call the same function, or let's say we use a helper function, and
In this, why do we need helper function?
because we need to update the count or
So you can
something
return
like
that directly, isn't it? Count paths root to leaf. From left, are there? From right, how many paths are there? Correct. Here, since we are not changing I and j, here boundary is only one. When root becomes null, return if root is null. If root is a leaf, then you return 1. Correct? If we want to check, we can do that. If root dot left is null,
And root dot right is not now return.
now you can return 1. But ideally, you will realize that this case is actually redundant case. If you don't put, no, sorry, this is not redundant. This is important because otherwise everything will be 0. So we have to put leaf always says there is one path from me to me, and then it percolates that answer back. So this, if you see, this becomes our base case. This becomes boundary case. Same problem we did on 2D matrices. We are talking about on trees. This is binary tree. What if this was n-ary tree? Here, n-ary tree would have, it would have map int this is how we can represent one form of n-ary tree. Here we know the children are going to be looped over, right? Now all the backtracking problems we have done so far, if we convert all of them to counting, path counting problems, you can visualize them this way. In phone, we did a problem, all four strings of phone sequence you have to generate. Somebody gives you a number and says, tell me how many strings are possible. Don't print all the strings, just give me the count. So we have to think recursive and give the count, right? One more similar problem for your exercise. Give max sum possible starting from origin to bottom right in matrix. You can move right down diagonal. If this is your matrix, this time problem statement, just see it's little different. We are saying consider all the paths, but you have to give the max sum. What is the max sum? You can think of this considering all the paths.
29718. Yeah, 29718.
29718. That means whenever we go to any node, we are adding that. This sum 819789716 25 27. If this is the matrix given to us, we should return 27 as the answer. Right? So can we think the same way, recursive way? And for now, when we are proceeding ahead, we will try to align to same direction. What we will do, let's make it a habit, since R and C are given, let's make it a habit to always come from the back side and go up, so that we do not worry about passing 0 0. Right? So taking RC coming from the back side, think of original function signature, what you will return. What you will return is,
I have a bottom-up DP solution for this.
yeah, bottom up DP we will come to first. We have to find recursion, because once recursion is defined, base cases are defined, bottom up is easy to code. Correct? All that you have to visualize first. So what we will do is go ahead with this approach, define recursive formula, base cases. Once you are done with this, I believe when this is done, top down or bottom up DP we can code on our own. Earlier 3 problems that we did, we intentionally gave you the formula and base cases, and we said, okay, let's practice converting that to DP. You remember those 3 problems we did that way. Now we are saying let's cover the remaining part, thinking of the recursive formula when recursive formula is not given. So here this is the problem statement, and follow it as a guideline, not mandatory, that we will try to start from back and reach origin. In matrix, whenever we are solving the problem, we will try to come from the other side, so that we can avoid the need of passing 2 additional variables to our helper function. Let's do.
So if we start from back and go to origin, the what we can do is like we did the bottom and right calls, or this, let's say, top and left calls, and added the count in the previous question. what we can do
Yes.
here, there will be two values returned, and we can store the maximum value that has been returned.
Awesome. Yes, Prakash. So you are able to visualize what changes from previous problem to this problem. In previous problem, we were returning the sum of left and right answer, left and upper answer. When we are coming from the back side, from last element of the matrix, we said in order to find our answer, if 8 wants to know how many paths start at 8 and end at 2, it said I'll ask upper guy, I'll ask left guy, I'll add their values and I'll return the sum. Here you will ask the previous guy, you will ask the left, and you will return the max. You're still missing some small thing. Yeah, okay, you ask. You get three answers. Answer, up answer, diagonal answer. We are returning max of 3. Max plus this value, because 8 you cannot ignore. Right? That is important thing to visualize. 8 is also part of the path, so 8 has to add. So now we see the way we are using the recursive return values, we have to add current value also. This problem is given in various ways. You are given a rectangular field, at every cell there are gold or there are coins kept. What is the maximum number of coins you can collect? Problem is same, just the rewording done for that. So quickly let's define the recursive formula, or let's do that together. You are able to visualize. Count of, no, this is max sum. When we write in terms of recursive formula, we give as matrix. What is max sum ij representing here? No, what is this value representing? Because if you are coming from top to bottom, it will represent something else. Bottom to top, it represents something else. So we have to understand what it is representing.
Row length, column length.
Max sum starting from where, ending where?
It's a row length and column, right?
Starting from ij. What is end cell? 0, 0. It's important because it should convey where we are going. Otherwise, when we are, we will be confused, +1 or -1. So we are saying every cell we are defining what is the value for this cell. If from this cell we have to go 0, 0. So we are saying this should be max of max sum
I minus 1
j.
j.
T is total number of column. We do not bring that in this. Yeah.
Max of ij minus 1.
T values it will be.
Max of I minus 1 j minus 1. ij minus.
If you are going from back to up, this will be the formula. If you come back front to back, it will change. But both are valid recursion.
Why are we taking this I minus 1 and j minus 1?
Read this line, Prakash. I tweak the problem statement saying this time you can go in 3 directions, not only 2. Why we are saying this is backtracking? Because we have multiple directions to go in. And backtracking is also recursion.
But
What is the base case?
in Java, you cannot compare 3, right? 3 values at a time. So we have to take
If you
2.
want to compare 3 values, you cannot. So what do you do?
We use 2 for
2
both
values at a time.
and compare
Or
it
when I
for.
wrote max here, I assume we can write our own max function comparing 3 values. Right? Again, this is not the perfect code. This is just a pseudo code so that we are to visualize what we are talking about. What is the base case here? In 0, 0, what do we return? Which value? Value present in 0, 0. So you can say this is directly matrix of, call it ij or 0, 0. Because when we reach 0, 0, 0, 0, we will say I am the last node, so my answer I am giving you. You can add to your path whatever you are. Correct? What will be the boundary case? Boundary is important because when 5 goes and asks left and up, 5 will make unnecessary call to up also. Even though it is invalid, it will still make a call. What should upper guy return so that it gets ignored? If it returns 0,
I less than 0, j less than
If I
0.
make all the values in the matrix as negative, if upper guy returns 0, that will anyways be higher than left guy. Int min or int max? Good, but what should it return, min or max? If it returns max, we will say hey, that's a better answer. So it should be int min. So this is, in matrix case, this is important. So you say max sum of ij is int min if I is greater than equal to, we are going from backside, if I is less than 0 or, right? Huh? Yeah. In first line, we have to add mat of I, j also. Correct? Yeah. And this problem we will be coding on mentor. So the thought process is very important. Once we nail that, you will see that it becomes very intuitive to think recursion and math. Correct? And now same problem, if I modify, if I say some cells I am filling zeros, if you have 0 in a cell, that path do not consider. That becomes another boundary case. If current cell is 0, what will we return?
Int min.
Int min, because we want that to be ignored. This is not a valid path, discard it. So that is called like grid problems with some restrictions, some constraints in them. Right?
Sandeep, why we did that int min? Like, can you please repeat that?
Why we did that is because from 8, imagine from 8, 0 we cannot traverse, 1 we can traverse. It is trying to find the max answer. So 8 will get some valid answer from 1. It will still make a call to 0. It will get some answer from 0. But we want to discard the answer 0 is giving. If we return a minimum value, since we are calculating max of these two, that will be discarded, isn't it?
Okay. Okay.
Because
You mean to
maximum
say,
of the
you mean to
integral
say like,
minimum value and yeah.
so you mean to say when we reach the topmost row,
Yeah,
that's when we want to discard that?
that's right. Because when we go out of bounds, we want to return a value which should be ignored.
But anyway, we check with the indices, right? Like why we do the int min again.
Yeah. Huh? Okay. Right. Okay. No, we are returning minimum. Sorry, we are returning a minimum value from up and whatever value we are getting from left side. What is the least value you can get from left side? Your return type is integer. What is the minimum value you can get from the left side? Int min. From up also you are returning int min. When you do max of these two, what will you return? Int min only. That means left is getting preference. Now you say left side is all positive and very high value. When this guy returns a value to you, it is higher than int min, right? Now if you do max of that value and int min from above, what will you end up considering? Which will be the preference to the value you actually got. So this is the way you are discarding one half. You are saying because it is int min, anyways max function will discard it. So it's a trick that we use. Answer to your question? If you are filling from bottom up, yeah. Mm-hmm. No, when it is 0, you will fill int underscore min only. You will not even go recursive. That's the boundary we are hitting now, right? When you see, if the problem statement I tweak and say wherever there is 0, you cannot move forward. So 0 should not make a recursive call. If it is 0, its answer in the final bottom of DP matrix should be int underscore min. Right? Okay. So This is the way to think recursion. You want to think of one more for practice? That's not a problem we are doing today, but it is still helpful to have one more exercise where we can think. It's not a 2D DP. We'll do string DP separately, but there is a string DP question that I'm putting here. A, B, C, B, L. Here given the string, and question that is asked is how many minimum characters we should insert in the string to make it a palindrome. In this string, return minimum characters that we need to insert to make it a palindrome. So how many characters do you think we can insert and make it palindrome? 4. What are those characters and how you will make it?
We need only 2, right? A and L.
BCBA. Okay, this is with 4 characters you are doing. We asked for minimum. So Prakash, what is your answer?
We can insert L between A and B and A at the end.
L here, A here. Will it become ALB, CBLA with 2? Anyone with better answer than 2? And imagine this was a shorter string. If I write a string like abracadabra and ask how many minimum insertions to do, that's where we want computer to solve these problems. We just need to figure out the recurrence and then we need to see like how to solve. So in order to think about this, I have a string in my mind, but I'm not revealing it to you so that you can think like computers. I ask you what is the minimum number of insertions to be done here to make it a palindrome. But like computer, you can look at 1 or 2 characters at a time because computers also see those indices. And keep in mind, we are not modifying the string, we are just counting. So counting problems, typically we do not have to actually create a path or create a string. We just can take some estimates and go ahead. Now, if this is the string, I'm asking you what is minimum number of characters you will insert to make it a palindrome. At one time, you can ask me 1 or 2 characters I can give you. So what characters would you be interested in knowing? Okay, let's say I give you first and last character. They are AA. Okay. So what Arun is trying to say is if first and last character are same, then we don't have to insert any character so far. The final answer will be answer of the remaining part of string. Can we make a recursive call with the middle part of the string? How do we define part of an array? By passing left index and right index. That way we can focus on it. You remember we did some problems, divide the array in 2 parts, make a left call, right call, where we were passing left and right. Now with that we see first and last character are same. If this was your L, this was R, you are going to figure out the answer for L plus 1, R minus 1. Give me answer for that range. And what will you do with that answer? Is that final answer or you want to do something addition or subtraction to that? No, you make a recursive call and let's say that recursive call gives you some answer. That will be your final answer. Does everyone agree with that? Yeah. Let's say this returns 0. 0 insertions are required to make it a palindrome. In between string is CBC. What is your final answer? With total string also answer is 0. Your sub problem said 0, you say, oh, my answer is also 0. Because I made sure I am equal to the first character. In this case, it is straightforward, right? Now let me tweak it. Let's reverse. Go back where you asked the first character and I said this is not A. Now what do we do? This is A. This is C. I revealed first 2 characters. Now tell me what will be your answer.
The answer would be the return value of the recursive call plus the character in the left and character in the right.
L plus 1 R you are saying that I will want answer for this because you are assuming that you have inserted A in the end. Can we say that? Because if you insert A in the end, one insertion has already happened. Now let's find the cost of remaining. This is one alternative, one option that you had. You could have inserted A in the end and you will try to get some answer here. Does that make sense? But is that the only choice? Or if you put C in the beginning, one insertion already done. You have to count that and then.
What if we do 2 plus L plus 1 R minus 1?
2 will be more, right? You're inserting A in the end as well as C. Let's take a look at few examples. If let's say it is A and C, if this was your original string, when you saw A and C, they were mismatching, you said I need answer by, if A I have inserted here, my remaining string is CBBC. You have inserted A in the end, so your answer for 1 plus answer for this. And second option you said, if I insert C in the beginning, then remaining string is ACBB and 1 plus. In string problems, it becomes little difficult because we have to see, are we missing any option? Ideally, when you don't look at this, when A and C are there, you are saying there are two choices. I can insert A in the end, it's my one choice. Maybe that can give me. But if I insert C in the beginning, there is another option. I cannot give my answer until unless I explore both the options and find max of. So DP is like backtracking. It says go in both the direction, get all the answers and return it. But DP optimizes it. Right? In this, we want to see how DP is optimizing and where it is DP. How do we say it is DP? Let's see. Initially, your string initially was 0, 5. Let's say it's a 6 length string, 0, 5, and they are not matching. The worst case we are looking at. If 0th index character is not matching 5th index character, then what do you do?
1 5 and
Recursive calls.
0 4.
0, 4.
4.
You typically go ahead and say, let's see what the recursion tree is looking like. Is there any overlapping thing? And we will find that sooner. And this becomes
2 2 4. Sorry, 2 5 1 4.
This becomes
It's 2. Sorry.
2, 4. Let's go from here.
But this is not necessary, right? That it would make two calls, two different calls, because
It is
the
not
character.
necessary it will make 2 calls. That's true. But we are considering worst case only. If it was not matching anywhere, 1 4 will become 1 3. One overlapping sub problem we have already seen here. Here also 2 4 2 4. If we continue going down, here can I say left of this will be 1 4, right will be 0 3.
Again,
When
DP.
this tree, to some extent, we start seeing the same recursion call happening with same values. This property is called, we are having overlapping sub problem. Same sub problems we are encountering again. Right? And that's the perfect example where we say it's a DP problem. So in these problems also we can think of backtracking solution. But when we submit backtracking, today you will realize when you submit on mentor pick, backtracking will give you time limit exceeded, and then you have to think of the DP solution. And today we are practicing, if we can think of recursion, bottom up, top down are no different. Like we can code anything with ease. So these 3 examples help us understand DP, correct? So we will park it aside. Practice we will come to later. So today my goal is, first we discuss all the concept and last 2 hours we spend only on coding. So this way we are clear. We have used matrices and now we try to use matrix as a tree. Because from every cell we have 2 directions, 3 directions. So we see matrices are not only matrices, they can be seen as tree also. Binary tree or any other tree? Huh? Max 3 ways. From any cell we can go right, diagonal, down. What if it's the central cell? How many options does it have to go to?
4 options. Actually 8.
8 options. Think of it when you are in a matrix at this cell. You have 3 neighbors above you, 3 neighbors below you, 1 left, 1 right. So ideally in matrix, you can go to 8 directions. We will do 8 direction problems also, but we will gradually reach there. Right now we are trying to keep it to 2 or 3 directions so that we are gradually reaching our goal. Right? Next concept that we are talking about, it's little different. And
one question. So the previous problem where we have discussed the maximum sum of the
yeah, maximum sum path.
so that is a bottom down approach.
Okay, so good question. In matrix, when we are coming from 0, 0 to right, origin to what do you say, bottom right, or going from this to it, this does not define top down or bottom up DP. Top down or bottom up DP is simple. If you have a recursive formula, when you are finding the answer, you are starting from base case, then it is bottom up. If you are starting from actual problem, making recursive call and making your answer, that is top down. Right? So DP should not be correlated with in matrix where we are starting. So in matrix, it is possible you are starting from bottom right to up, and you can code both top down as well as bottom up DP, because it is based on base case of the recursion, not on the matrix. Clarifies? Okay. Now there is a small thing which we had been using so far, but we never talked about it. Sorting and comparator concept. So if we have an array or a list, every language provides built-in functionality to sort them, right? So here we will talk about a basic sorting algorithm. Let's say I have an array of size n. I want to sort the elements of the array. What should be my function signature for sorting?
The void
Void.
sort of array if C or C++ means we should pass the length.
This is how we will write our sort function. If it is Java, we don't need to give size. N is not required. C# n is not required. Python n is not required. But in C++ we require n. So this will be our function signature. Why we are not returning the array? Because when we pass the array, if we modify anything in the array, it is reflected back. So we say we will modify, we will rearrange the elements in the same array. Right? So here we talk about an example called selection sort. What is the idea behind selection sort?
Wrapping the minimum index and normal order.
Okay. Imagine you have few numbers, and imagine these are playing cards. You have to arrange them in sorted order. One way is, out of all these, I will first choose one and I hold it in my hand. I pick it from the table. Imagine they are lying on the table. I pick and hold in the hand. Then what will I get next? Out of remaining, out of remaining, who is the minimum? 2. I choose that and keep in my hand. So this is taken, this is taken. So what we are doing out of remaining cards, what is the key thing that I'm trying to do? Out of all the cards on the table, which one am I picking? Minimum. So I can say out of the options that I have, I'm selecting an option. So selection sort is that. Selection sort says you choose and then keep in the proper place. That is selection sort. So what do we mean by selection sort? If you have an array, in an entire array, find the minimum element. If it is one array, 5, 9, 2, 4. In this array, we know how to write a function to find the minimum element. Typically, we write that function as, that function will return the index of the minimum element. Which index it will be found at? 2. After we find that index, we swap it with the 0th, because first we are filling 0th index. So let's swap them. It becomes 2, 9, 5, 4. Correct? Now out of the remaining array, we again find the minimum. This time we swap that minimum with first index. That every time when we are proceeding, we are choosing the element. That approach is called selection sort. Correct? Ideally, thought process wise, if I say find minimum element index for I0 to I find the minimum element index. What do I do after I find that minimum element index? Can I say this is from I to n minus 1? Because every time we are finding minimum element in the right side, we are not considering existing elements. Then we swap idx with I and do I plus plus. Correct? This is the selection sort. Now, what is insertion sort? 1, 9, 2, 5, 4. Earlier, we were becoming choosy in picking the card. Now, let's say I say all the cards are in reverse. You cannot see the numbers. So, whatever card you pick, you have to take that. So, in playing cards, we do that. Reverse card, we pick one by one. Right? So, we pick first card. We are not putting any criteria in selection. We keep it in hand. Imagine the first card I took is 2. So I keep it in my hand. Now the next card that I am picking, if that is 4, what will I do with 4? Compare with existing cards in my hand and see where it should go. So now the focus is not on selection. Selection is random now, but focus is on insertion. So insertion sort says that we will insert in the right place and we have to find the right place for it. Correct? So that is difference between insertion and selection sort. Many a times this gets asked to college students in interviews that what is different between these two. People say in selection we insert the minimum element into the array. If you are inserting, this is the insertion sort. That's where the confusion comes. Interviewer says, okay, you are inserting the minimum element, so you are doing insertion. Then how insertion sort is different? Then we get confused. Yeah, insertion sort also we insert, in selection also we are inserting. So that's to disambiguate it. Okay, so here when we write selection sort, we were talking about writing a function, find the minimum element. In order to find the minimum element, can I say we do the comparison? Right? We do the comparison, and that comparison depends on the data type. Will the same logic work for string array? Yes. What will change in integer array versus string array? How do we compare? If a is less than b, that comparison for string will be not with less than symbol, it will be with some other symbol. If that comparison function we can take it out, keep it separate, then same algorithm will work for anything. So comparison function is typically taken out, right? So reason I discussed about this is so far we have been using in C++ a comma a plus n. This function we have been using. In Java we have been using arrays.sort, directly give array, or collection.sort, we give a list. This was by default, these functions arrange our integer array or string array in ascending order because these are built in for built-in data type, they work as it is. This sort them in ascending order, strings lexicographical order, integers normal natural order. But what if you want to sort them in reverse order? This sorts in ascending order. What if you want descending order? Yeah, how?
We reverse the string, sir. We'll reverse the string.
After sorting reverse. Okay. Yeah. Yeah. All these functions take a third argument, a comparator function. They say we give you the freedom. You give your comparison function. You decide the order because we just need how you are comparing two things. Give us that order. We will call your comparison function and sort. Right. So we will ideally, yeah, we could sort and reverse. That is one way, but we can directly use the built-in way. This syntax, this is important to know that this comparison function we can provide. The syntax is already posted in MentorPick. In notes, it will be shared with you. But knowing this concept is important. We simply call sort. Be aware when this sort is sorting the array, it will call your comparison function multiple. Do you agree? Whenever it is doing the comparison, If it is insertion sort, there will be different number of comparisons. Selection has different number of comparisons. That's where complexity goes high. So your comparison function taking out is the goal. Right? And same concept we are going to use in the next data structure we talk about. Sorting algorithms we will do different separately. We have a dedicated session for that. But here takeaway was be aware of insertion and selection sort and their difference. Because we will not be coding those. Those are easy ones. We will be coding mainly quick sort and merge sort, because that's where we make mistakes. They are not going to be interview questions, but we should be comfortable in coding because that pattern gets applied to a lot of other problems. Okay.
When we use any of this function, this will add it to the time complexity.
Good question. Yeah, when we use any of the existing functions like this, n log n is their time complexity. So whenever you are doing time complexity analysis and you have used inbuilt sort function, you will account for that this takes n log n. Because most of the libraries, they claim that worst case they are n log n. Yeah, but you will account for it. Internally, yeah, they are using quicksort or merge sort. Yes, mostly they use hybrid. There is some sort of logic. If n is less than 25, call insertion sort. Ideally, you can also build your own insertion, your sort function, where you say if n is this, use this algorithm, otherwise use that algorithm. We call it a hybrid. Some implementation will tell you, yeah, they use quicksort. Some will say that we are not telling how we internally do it. Yeah, but imagine they are hybrid, but they claim to be n log n. Right?
Sir,
Yeah, Badri.
sir, the last sorting function, no, sir, a collection dot sort. In which language is that
That is
built-in
Java.
function? Java. Thank you.
They are Java. This is C++. It has a Q sort, but I will recommend not to use that. It becomes confusing at times. If you're using C or C++, both are same. Like we just have to change the compiler to C++. Most of the online platforms support C++ if they are supporting C.
Sir,
Use
you
this.
told that in sorting time complexity, n log n is the minimum, no, sir.
Yeah.
So quicksort applies n log n, right?
Yes.
Yes.
We have order n sorting algorithm also, which we call count sort. We will talk about that. But it is applicable to special cases. Only if the range of array value is known. That's where we apply count sort. So it is not generic, it cannot be applied to any given array. So that is the best known sorting algorithm in n that we can sort. Right? Okay, so next thing that we are talking about, it's a concept that we are all are aware of. So we will quickly talk about and proceed forward from there. An array can be seen as a tree. Remember we talked about this concept, complete binary tree. If you have an array 1, 5, 9 to 6, this array can be seen as a tree. Sometimes this array is told from 0th index. Sometimes in programming problem it is given as an array. They say array is filled from first index. So today I will talk about from first index. Can I take an array of size 6 and use only index 1 onwards? So this is an array of size 6. I'm not using 0th index. I'm using index 1 to 5. It's possible to do that. I say this array is representing a tree in such a way 1 has 2 children, 5 and 9. 5 has children 2 and 6. This is a complete binary tree. Complete binary tree means fill from left to right order. Don't leave any gaps in between. Right? This array is given to us. We should be comfortable dealing with this array both if it is 0 index based or 1 index based. Little formula changes happen. In this, if I say parent index is given, what is the left child index if array is 1 based?
2n, and right child would be 2n plus
1
1.
has 2 children, this and this.
5 and 9, right?
Oh, sorry. So it has 2 children, 5 and 9. So left child formula will be if this is 1, its left child is at which index? 2.
2n.
So left child formula, can we say it's 2 into parent? Right child? Does it hold good for others also? Let's validate. 5 is at index 2. 5's left child is 2, which is at index 4. It's double the index. And its right child is at into 2 plus 1. Right? So this holds true. Now, if this array is given to us and somebody says what you have to do, you have to let me modify this array to some value 4. Yeah. So in this array, I have made root to be 4, 4, 5, 9, 2, and 3. We say every node is bigger than its children except one. Every parent is bigger than the children except one. What is the node which is violating this? 4.
Root node.
Make it proper. We want to make it in this array, we want to make it such a way that here also root should be bigger than its children. This is the operation we are defining. We will give you that index in the array. This index in array will be given, which is violating that property, and there is only one such index. We say, can we get it to a situation where root or parent is always bigger than children? How do we do that? Compare root with its left child, compare root with its right child. Out of these three, who deserves to be in the root position? The biggest of all three should be at the parent position. This operation of taking a node and bringing it down recursively, we continue to do that. This operation we are calling, this is max heapifying. We are heapifying down, correct? And now we have to figure out when we are at a node, how we are going to left, how we are going to right, and how we are bringing it down. And that recursion we have to think of, that base case we have to think of, which we will nail in the coding time. Okay. Concept is this, and today we will master this concept. And why we are doing this concept is because this is useful. Heap is useful in solving a lot of problems. And most languages provide inbuilt heap. Like we have used stack and queues earlier, right? We use inbuilt stack, inbuilt queues. Same way priority queue is also inbuilt, except C#. C# doesn't provide priority queue. So we have to code our own priority queue. And what are the functions priority queue gives? It gives an insertion function. Inside priority queue is an array only. When you insert, now you see after this readjustment, do you see this is a max heap? Max heap means parent is always greater than the children. Currently, whatever we are seeing as a tree, forget about the array, as a tree, whatever we are seeing, is that a max heap? Correct? Now, if that was an array has more capacity. I say do an insertion in the max heap. Where will the insertion happen? We are inserting, let's say, 1. Left of 4. Okay, 9 we changed. 9 we replaced. Left of 4 we put 1. So in insertion, what we do, earlier the size of the array was n. Now we make it n plus 1 and we insert a value there. Size we are changing, capacity is still more. This is clear? So array had more locations, but whatever we are filling in the array, we are treating that as the used values or the size of the array. Correct? So when we insert 1 here, after inserting 1, what should we do? We should try to take it up if this is greater than its parent, because this is the only node which would have caused problem to the heap structure. Correct? If in place of 1, if this was 7, we first do the insertion and then we try to take it up. So from current node, we can calculate the parent index. How do we calculate parent index here? I by 2 here will directly be the parent. Think about it how. 2 has a parent 1, 3 has a parent 1. Divided by 2 is directly giving the parent index. Right? Okay, so we compare this with parent. If parent is smaller than this, then what do we do? We swap this and parent, and that parent again we recursively compare with its own parent till we reach the root. This is called heapifying up. Think about it. Should we compare in this case when we are doing insertion? Should we compare with the other child also? No need. Why no need? Before inserting this element, it was already a max heap. If it was already a max heap, the current node, the current parent was already bigger than the other child, right? If that is already bigger, then other node does not need to change. You are bringing only bigger value up, right? In case of also, earlier if it was min heap, now you are taking the minimum value up. So when you are going up, you have to go only one path. When you are coming down, you have to consider both, but still you will go down one path, which makes it log n operation, both sides. Anyways, when you try to code, you will visualize that yourself. So insertion is log n operation. Deletion of minimum. How do we delete the minimum? In min heap or max heap. In max heap, where is the maximum value lying? Always root, because we are saying parent is always bigger than the children, and this holds true everywhere. So if root is the max, we want to delete the max element in max heap. Similarly, in min heap, minimum will be in the root. So deletion, what we do, we swap that with the last value. Last value comes up. We decrease the size of the array, and then we perform heapify down. Right? So these two operations are key operations. Heapify up, heapify down. If you are able to write those recursive functions, we are all good. Right? So delete min is this. Get a minimum value. Where will be the minimum value in min heap? Root. Root will have maximum value in max heap. So this will be order of 1. Size. When you are maintaining an array, when you are inserting, do n plus 1, deleting n minus 1, return that n value directly. Don't count. Can we say this we will make it in order of 1? Because size variable we are tracking. Empty or not? Based on size we can tell. So this data structure we build, ideally not a new data structure, but the benefit is the complexity that it provides. It's better and faster. It will be applicable to a lot of other problems we will do. So today we will master this data structure and we will try to see where it is applicable. When we are putting values in min heap or max heap, ideally the comparison is what we are doing. Can I say that? We are comparing with the parent and moving it up. This is similar to sorting. If you can separate out the comparison function, same array can act as min heap or max heap. Compare function is controlling it. It is min or max. Right? So most of the inbuilt libraries that we use for min heap, max heap, we are given that facility of giving that comparator function. So they are closely related. And when you do the insertion in inbuilt data structure, imagine you are using inbuilt priority queue of a language. You just do the insertion, it automatically readjusts and reaches there. You don't have to do anything. We did a jumping number problem. In jumping numbers, a lot of people face the problem. Satya was struggling last night with that. The problem was that we are generating in some order, but expected output is a different way, right? You use queue for that generation, right? And later on we sorted it. Everyone is able to correlate to that jumping number problem. We were generating jumping numbers, putting them in a list, and then printing them. Now try to visualize that jumping number problem in place of queue. If you use priority queue, same level order traversal, in place of queue, use priority queue. Give a comparator function which compares their lexicographical order. Then the output you would have got in the same order. Right? Because heap internally does that readjustment. It always gives you the minimum value lexicographically in that case. So if you would have used a priority queue with string as a data type, it would have given you lexicographical sorted output. So it's just replacement of queue with priority queue and your problem is solved. It is better? Yeah, it will be better. Reason is when you are sorting later, you are doing n log n. But when you are inserting, it is immediately sorting. Until that time, not all the values are in. So log n for smaller values will be lesser. If you have only 5 values in the priority queue, that sorting is faster. But in the end, if you sort all n values together, that will be slower. Big O wise both will be same, yes. Yes, Lego wise both will be same, but your code would have been simplified a lot. You just replace queue with priority queue. That's it. Yeah, okay. If you have done recursive, he did in a level order way. You can do both ways. Yeah, ideally he used the recursive way. With 1, generate all the jumping numbers starting with 1. Because the constraint was given, print all the numbers less than a given value. So your boundary case would have been if it is less. But yeah, we will see now that we have both the ways for any problem that we solve, either recursive way or the iterative way, which is level order. Okay, concept of heap is clear. Okay, so this we will talk about when we are comfortable with heap. Some of the applications today we will see where we apply. Like we did DP, we saw the 2D matrix application. We will put some thought process, and tree we will graph we will introduce toward the end once we have done this much. So far whatever we have done, if we quickly summarize, we started with the 2D matrix understanding. We started seeing in 2D matrix how the options are considered, correct? And then eventually we try to see where they lead to backtracking, how that backtracking enters dynamic programming, and how do we convert our recursive formula to dynamic programming, right? That's the territory we covered. We talked about heap data structure using array in a different way. We just have to visualize in a different form, and we will be coding and making heap out of a given array. So any doubts so far? Okay, valid point. So what is priority queue? It's min heap or max heap only. So priority queue is a different name for min heap or max heap. So whatever we are talking about, call it either min heap or call it minimum priority queue. It's the same. So priority queue concept is, in queue you put in some order, you get in the same order. Priority queue says if I put a high priority item, it should immediately go to the top. And queue heap is doing exactly that. It takes it up. If it is a max heap, we say the high priority goes up. If it is min heap, we say P0 means it should go through the top. Where is it used in real world? Yeah, scheduling algorithms use priority queue. When your processes come into existence, in Java you create a thread, a process, you set its priority, and it goes up faster. Ola has a ride later feature. You can ride later. You can book a cab for tomorrow morning, right? And before the cab is assigned, it sends you a SMS. 15 minutes before the cab has to come, it sends an SMS to you. So if all the bookings that people are making, if they are put in a priority queue, whatever time is approaching, imagine it is coming, that will always percolate on the top. They don't have to search in the entire list. So in priority queue, if you keep updating the values, they will always keep going up and up. So that is rebalancing, that is readjusting. So yeah, that is also a scheduling problem ideally, that what is the next task that we have to do. Okay, so we will take a 15 minutes break here. We will start coding these problems, whatever we have discussed. And if you get stuck, we'll take your questions.
This conference will now be recorded.
Okay, this week we have 6 stars of the week. Can we clap for them? All of them are here. Anybody missing? Yojit is here. Okay. So we have some these for you. Some stationery kit. Last. I mean, for you, I have one less, but I have something else. If you are fine with that, or we can get another one from another. Huh? No, you have another alternative also. If you want to go ahead with that, I could not get 6 pieces of that. Yeah. So there are 2 to compensate for that. This is everything. Planner and this is some full paper weight. Yeah, and next week onwards, we are changing the format of star of the week. So next week onwards, there will be less assignments on mentor pick, but we'll keep some goal of interview bit because we have to start moving problems there. So every week we'll keep a goal of a score that you have to attain. If you attain that score, doesn't matter where you are on leaderboard so far. That's a chance for everyone to get there and get into this list. So it will be now, since most of the concepts are covered, we should try problems that are out there in open and that have harder test cases. So I'll update on the group how we are going to proceed from next week onwards. Yeah, next week onwards, this is mentor pick is not the criteria for star of the week. Yeah, so let's go to mentor pick. 7 problems.
Yeah, I submitted my solution for the first question.
Okay.
That is min cost.
Mhm.
I just used basic recursion and I'm able to successfully submit. Now
Okay.
I'm trying to convert it to top-down DP and I'm not able to figure out where actually to define the DP array.
Sure. But all the test cases passed for you
Yeah,
in
simple
basic
backtracking.
recursion.
Yeah.
Okay. Yeah, so the first problem, okay, since it is a backtracking problem, I think this does not have harder test cases. So even if you submit backtracking solution, that will be passing problems which we have categorized as dynamic programming. We have made sure the brute force solution or backtracking solution do not pass all the test cases. So Prakash, you are fine with that for now. You can proceed further. We will do the same problem in DP variant also. But right now move to the next problem.
Okay, sure. To be
This
leading that.
conference will now be
Okay.
recorded.
If
Sure,
you,
so you want to know?
yeah, just something that is I need to know, not the whole solution.
Got it, got it. You are basically seeing how do I convert my
No,
backtracking
no.
solution to top-down DP.
See, in the if you go to my solution,
Yeah, this is your
yeah,
solution only.
yeah, in line number 145, the recursive calls that I'm making, I will store them in an DP, okay, that is 2D matrix.
Mhm.
And the thing that I'm struggling with is the place where actually I will define the array for
Okay,
the
so
DP.
this is where you can define Prakash.
Yeah, but there, how will I get the rows and columns that are needed?
Rows and columns will be based on the problem statement that you are solving. If I go here, let's see. This problem should give you some constraints. Oh, this is not giving the constraints. Yeah, ideally for now you can assume Prakash there is 100 by 100 matrix at max.
Okay.
So you will
Okay.
define the matrix here,
Hmm.
initialize the matrix here, and use it here in this.
Okay. Yeah, that
So
makes
this will
sense.
give you a fair idea.
And one more question. When we are defining the DP array, shouldn't we actually keep the dimensions as the one which is given in the question? So let's say we have array A whose dimensions are
Uh-huh.
R and C. So shouldn't the DP array be the same?
No, ideally DP array's dimension you decide based on in your helper function how many variables are changing. How many are changing here, Prakash? Out of these
Uh,
3 input parameters?
just two are changing.
If 2 are changing, it will be a 2D DP problem. If 3 are changing, it's a 3D DP problem. It's that way.
No, no, no. What I'm saying is the dimensions. How do we decide? Let you said that you can use 100 by 100, right? So why not
Yeah,
R by C? Because that array wouldn't be used in other test case anyway, right?
yeah, yeah. You can go with R by C also here. That is fine. Reason I said 100 by 100 is like typically based on the constraints. Ideally, this problem statement is not complete. If problem statement says max matrix you will be given, max R and C you will be given will be 100.
Okay, got it.
So
In
it
that
was
way.
like, okay, take the max capacity and go.
Yeah. Okay. Thanks. are
This
needed to
conference will now be recorded.
Just a
find the
second.
total number of unique paths.
Yes.
So if the all the array values are same, then all the paths would be considered same, right? Let's say
Yeah.
there is a square matrix given 1 1 1 1 1. So
Yeah.
every path should be 1 1, right? So is it
Let
a
me see
unique
the
path or
question.
not? Okay.
Return how many total unique paths are possible. First, try coding, assuming we just have to count the paths.
Okay.
Yeah. Mostly it will be that problem. But your doubt
Okay.
is correct. If everything is same, then there is only one. But I guess this is just the counting problem.
Okay.
Yes. Yes. Yes.
This conference will now be recorded.
Okay, so this is a solution that Amit has written. This was mean cost. In mean cost, we are returning int max as the highest value, correct? And you are going from the back side. What is m and n here? It is the size, and the way you are using it as. So if m and n is the size, they are not the indices. So if you want to access the current value, you should be m minus 1, n minus 1, so that you are going with the last value. It depends on what the parameters you are getting and how you have to use them. We can still work with this problem taking them as size. Yeah, Sairam. If we are doing this problem, here m and n is the size of the matrix. Then we want to figure out the min cost from one end to the other. So if we go based on that, first we want to ask that question to the bottom right element. Right? Manisha, we are discussing this problem that you are trying to do. In the matrix, we are trying to ask this element that you tell me the mean cost from you to the top. But what we are passing here is the size. Can we treat this as this size matrix? Then this size matrix will ask this size matrix as a sub problem. Right? So we go it that way. So let's see. So when this is the size, we are asking the question to m minus 1, n minus 1 element. Can I say that? Let me get rid of these cases for now. What we are saying is when this is the size of the matrix for which we have to give the answer, we will take the last element plus in this matrix, our answer that we want to figure out, this element is already taken, correct? Then can we say we need answer from this matrix because this is the last element of this matrix, right? And how do we make a call to this element now? Yeah. If this total matrix is of size m cross n, in this sub matrix, what you removed? You removed one row out of it. So what this remains is m minus 1 n, not n minus 1. Only row removed, columns remain the same. And okay, here Amit, you are adding to both, right? Can we do it this way? We ask both and then we add later. So yeah, we go with min cost m and n minus 1. This is clear. So we make two recursive call. Based on the size, we made first recursive call to this matrix. Second recursive call that we made is to this matrix. We say we need your answer because your answer will come from this guy. Upper guy, we say your answer from this guy. These two answers is what we are interested in. And minimum of these two plus current element is our answer. Now m and n is size. So what will be the base case? If size is 0, what is the minimum value we can get? M and n is size now. Or you can put case like if m is 1 and n is 1. M and n is the size, not the indices in this problem. If matrix is 1 by 1 only, what is your answer? Same element. What will be that element return? No. If matrix is of size m 1 cross 1, what index will be 0 0. That's the reason here also we wrote m minus 1 n minus 1. So you will say 0 0. Correct? And then there is a boundary also, because every time when you are reducing, if only one value becomes 0, if rows become 0 or columns become 0, then what do you do? If n is less than or equal to 0 or m is less than or equal to 0, then we say int max. Right? This is the case. Why we are considering this case is, imagine if this was the only matrix, this guy will ask upper guy and upper guy is not there. So let him return int max and this will discard it. This min function will discard it. Not random, we are returning maximum highest value of an integer.
Hello.
Yeah, Prakash.
Yeah, in the third problem, that is max CP5, we discussed that in the array, the children of the node are represented by the values at index 2n and 2n plus 1. So the solution that I have is we will compare the index that is given, which is wrong. We will compare it with 2n and 2n plus 1, and whichever is max out of those two, we will swap the position with that. Now,
Okay.
it may cause problem at other index, so we will have to check, right, that now the new node doesn't cause problem for its parent. So that's the
Right.
thing that we have to do here, right?
Yes.
Okay.
So you have to be cautious of the indices that you are dealing with.
Okay.
Should be saying max CP5 doesn't have C#. Yeah, should be for you. I'll send one thing. Shubhi, can you use this link? Here I have put C# code, and you can think of writing insert function on your own. NQ. I'm just pasting it here. C# code I will enable so that you are able to write from scratch. I did not pay attention that it's missing C#. Yeah, sure. Okay. Oh yeah, reading you will have to do, Shubhi. What you can do, the link that I have sent you, just go there, take the priority queue class from here, paste
Okay,
that.
sir, I shall do it.
Yeah, and you will need input format then, right? Input format is also not specified.
Yes.
Can we fix it, Arthur? Yeah. Number of test cases, number of elements. Yeah. Describe. Yeah. Should be we are fixing also so that we can describe the input format for you.
Okay, thank you, sir.
Yeah, found it? Or you did not, or you included diagonal? Yeah, so just fix it. Yeah, go with the problem statement because same problem statement get twisted in various ways. You can go only 2 directions, 3 directions, and both of them can have constraints also. Right now we have not put constraints. Yes.
Sandeep, we have not yet covered the generation of heap, right? It would be done later, or is it
Generation of
that
heap as in?
like we have given an array of elements, now we have to generate a max heap or a min heap? That is not
Okay.
covered yet, right?
Okay, Prakash is asking one valid question. He says, if array is given already, which is not a max heap, not a min heap, 5, 6, 2, 1. This array is not a max heap because it is 5, 6, 2, 1, right? We are writing a function called max heapify. Can I say, if we call max heapify from the last element of the array, from every element we are calling max heapify. Imagine if I call max heapify for 1, what will happen? Max heapify may we bring the value down, higher value. Yeah, in max heapify, what we do, if there is a lower value on top, we bring it down. Now, if I do max heapify at 1, max heapify down, what will happen? Nothing. If I do max heapify at 2, nothing. If I do max heapify at 6, it will compare, but nothing will happen. If I do max heapify at 5, 5 will be replaced with 6, and after that 5 will not percolate down. So there is a concept called, if you want to build heap from a given array, start with I is equal to n by 2, I greater than equal to 0, I minus minus. Max heapify in that array for that index I. Prakash, is this making sense? Because leaf nodes you anyways do not max heapify. If you do this, you can build max heap out of an array.
Um, I equal to n by 2. How are we sure that after n by 2 all will be leaf nodes only?
Good question. So try to draw any heap and figure out what is the first known leaf index. Here n is 5. What is the index of first known leaf? So
4.
ideally, if you see this, you understand calling max heapify on these do not make any sense for leaves, right?
Yeah.
So if you do n by 2, here you are getting 2 in fact. So if you start from 2 also going back, you will convert it a heap. So this is the thing I am using. Ideally, if you go with n also, if you go with this also, then also it will convert a given array into max heap. Do you agree with this at least?
Yeah.
Yeah. So making an array into heap is nothing but you have to call max heapify from backside, so that you are bringing every element down and converting into max heap. So that's an easy operation. That's the reason we did not talk about that.
This conference will now be recorded.
Okay, so Rahul asked this question that I'm not understanding why we are returning int max. This thing, right, Rahul? See, we have two choices when we are going out of bounds. Ideally, in a matrix, when you are at this element, it will make two calls. Imagine we are coming from up to bottom. So this has two neighbors to ask the question, right? Two choices we had. One, we do not make this call at all. Can we choose to do that? When we are making two recursive calls, I can check if the right index is out of bounds, don't make the recursive call. This is one choice we had. If we have to go ahead with that choice, this recursive calls that we are making, we can put a conditional thing there. If r plus 1 or I plus 1 or j plus 1 is exceeding the size of an array, do not make the call. This is clear? So what we decide, if we put conditional, it becomes a little complicated code, or we are writing clumsy code, it will not be shorter code. So what we decide, we say recursive call we will make without putting any checks, and the boundary case will handle that. Okay. So now you see, we have to find the min cost path down as well as right. You want to select which path? Down. Or the overall answer, you want a path with minimum cost. Can we say that? Okay. Down one will give you some answer, that is for sure. Right one will also give you answer, because I said we are still making a call. Even if it is invalid, we are making a call. Now we are saying, if we make this call, we know we are going out of boundary, but we want to do something here so that in such cases, whatever answer right gives, we can discard it. Here we are writing a min function. We are calculating minimum of bottom and right. What answer should we return from the right side so that it gets discarded if it is invalid? No. Right will also give you an answer. Bottom will also give you an answer. We want to do something in returning such that right answer, if it is invalid neighbor, it should always get discarded. In this you are able to see, but how will computer know?
Sir, we can just increment the I, sir.
Yeah, that's right.
We'll check another condition. If I double equal to m minus 1 and j double equal to n minus 1, that will be a separate condition.
His question is a little different, Abadri. He's trying to ask why we are returning int max. Imagine, Rahul, if I say I want this function to return a always, where a and b is int. I want this to guarantee when will it return a. Can you think of a value of b where this will always return a? Huh? If I make this maximum, it will always return a, because a cannot be greater than this value. A can be equal to this value. By making it int max, can we say it will guarantee it always returns a? This is what we tried. We said if it is invalid neighbor, let it return max, because if it returns max, this min function will anyways discard its value. That's a trick that we use, and that's how we decided return max. So whenever we are finding a minimum value, in boundary case we return max. When we are finding a maximum value, in boundary case we return min. So this is a way we still can make a recursive call, and boundary can still return a value and we discard it. So that was the logic behind it. Yeah, which one? Heapify? Okay, so heapify down you are writing. You are writing C# only. Oh, you have submitted Java code. Sure. So you got size. Yeah, resuming. Okay, sure. In heapify down, size will not change at all if you see, right? So you say biggest is IDX. After this also. Okay, ideally if we logic wise, if we talk about heapify down in an array, index and size of the array, these are the three things that we have. So what should we do when we are heapifying down any index? This is 5. This is max heap or min heap? Max heap. So let's say this is 6 and this is 9. This is 4. This is 12. This is 8. This is 11. So when we are heapifying 5 down, first we have to find a new parent. Who will become the new parent out of its children? 9. Agree? Okay, so we say let's bring 9 here and 5 here. But when you come here, shall we still go down or not? We should again find who out of them will become the parent. So 11 and 5 comes here. Now 5 doesn't have any more children, that's where we stop. So we have to continue taking the value down till it becomes a leaf or till it becomes a value which is greater than both the children. Huh? So your logic is that only. Okay. So how do we compare IDX with its children? First, let's say we assume max index is IDX. That is what you have also done. Now you will compare this with left and right both children. So how do you get left index? 2 IDX plus 1. Oh, in that heap is 0 raised. It was not given probably. What we are giving you, yeah, that's my mistake then. What we are giving you as a heap here, it's a 0 based array. It's not 1 based array. So your formulas will change then, right? Yes, I minus 1 divided by 2. Huh? Given array is 0 index based. So that was the thing because it was missing. Now one thing which is very important in this heapify is, let's say we get left index, right index. What is right index formula? Can I directly say this plus 1? By calculate again. Right? So left will always be 1 less than right. Now we say we want to find max out of left and right and root. Can I say if array of left index is greater than a of IDX, then who is the max index so far? I'm just trying to get who is the max out of 3. Same way, if a of R IDX is greater than a of IDX, then okay, a of max, sorry, a of mi. Here also we put a of mi, just for uniformity. Now, if, can I say if mi is not equal to IDX, only then I need to swap, otherwise I'm done. Right, so what we did, this was 5, this was 6, this was 9. First we assumed this is the max. We compared this value with left. We said if left is greater, then our max is left index. This is the max so far. We compared this AMI, this max with 9, and we say now right is the max. So we are updating. Now out of these 3 we got who is the max. If current index was max, we stop. If it is not the max, we say swap A, MI and IDX. And what recursive call do I make? I can go with recursion or iteration, right? I can go with recursion here. You have written iterative while loop, that is also fine. A, MI and N. So this will heapify down. But this code has one bug. This code has a flaw. Can somebody tell? See, if my heap was this, if this was IDX, heap has only 2 elements. Who is the right child for 5? It's not there. Am I checking that? I blindly say if 0 is root, 1 is left, I'm blindly going and accessing right also. So we should, yeah, complete, even this is a complete binary tree. Complete binary tree can still have a left child but not right child. Complete binary tree says you fill from left to right. There is one more terminology which is called full binary tree. Full says that all the children at every level will be there. So max heap is complete binary tree, not full. This is a valid complete binary tree. So what do we do? Can I say if L of IDX is less than N? This is like that boundary check. Here also I can say R of IDX is less than N and this. So this is kind of protection check, because if this is false, second one will never be evaluated, right? So then we have safeguarded ourselves. And yeah, if you feel comfortable, you can use iteration in place of recursion, which will be, we know, more efficient memory wise than this. So iteration I'm leaving as an exercise for people.
Sir, can you please look at my code? It is
Sure,
showing
Badri.
error. I did it by that conditional way only, sir. Min cost.
Okay. Searching for it.
Sandeep, can you please explain that concept L index less than n, the final condition that we put again?
Okay. So this was, Prakash, when you have a heap like this.
Yeah.
This is your index 0, this is index 1. Does it have a right child?
No.
If I don't put this condition, I will be accessing value outside the index, isn't it?
Yeah, you will be accessing the index out, but I'm still not getting how come R index less than n solves that thing, solves that issue.
If this heap is represented as an array,
Yeah. 0,
this is
9,
0, this is 1. What is the size of my heap right now? What is n right now?
2.
Now when I calculate R index, this came out to be 2. I'm comparing that with the size of the array. Because if this index is not there in the array, that
Got
means
it.
that's not a.
Got it. Got it. Got it.
That's why
Thank
it
you.
is less than. Badri, is spelling correct? BADRI?
Yeah, yes, sir.
It's not searching.
Sir, BADHRI, sir.
Yeah, Badri, what is the compilation error you are getting? Control each is end of a known void function. So you are not returning in all the code paths of this function. That's the error. Ideally, it says you should in every case. So in last case, you are not returning.
So the rest of the cases I am returning, sir. Is the function returning?
Now see, if you put return only inside if I say, if let's say, if n is 5, return 1. If n is 2, return 2. Can you tell me, Badri, what will it return when n is 10?
Nothing, sir.
So that is what compiler is saying. There can be a case where both these if conditions are not true, then you are not returning anything. So this is, you should return something. Another way people do is they can write an else. Now what will it return?
5.
If n,
Sir, if yes, 5.
so your code, you have just put if everywhere. So compiler is saying if none of these if condition is true, then you are not returning anything. That's the error. Just try to correct it.
Sir, so shall I include else if and else, sir, instead
Yeah.
of if?
If you put,
Yes.
there must be an else case in the end so that it
Yes.
falls in that. Yeah.
Yes, sir. Thank you, sir.
In the heapify down function that you have written using recursion, the mi that we are passing in recursive call, it is because that let's say we have swapped a and b node now,
Yeah.
and we have to check heapify down property only with the new parent, right? New node
That's,
that is with me.
that's
Okay.
because if you have compared 5 and 6 already,
Yeah.
now 6 should be compared with 9, not 5. So initially we assumed this is mi, then it changed here, then it change here. This is index remembering who is the max so far.
Yeah.
Sure. For which problem? Unique. Sure. So Mr. you are passing R and C as total. It is size. It's not the index, right? Who will return 1 to it? You are coming from the bottom to top, right? So which element will return 1 to it? First element. At that first element, what will be R and C? You have a matrix 3 by 3 whose answer you are trying to find. You are making call here and here. This will make recursive calls. This will also make recursive call. Who will not make recursive call? That is this, right? How do you identify we have reached here? What is R and C here? R and C is size. So can I say here when R is 1, if it is size, you have to compare it. When R is 1, C is 1, now you have only one element, 1 by 1 matrix, then you return that 1. If R and C were indices, ideally imagine if you would have written as a helper function and rather than passing R and C, you would have passed ij, which is R minus 1, C minus 1 as the first. So that is one difference that comes. If you deal with size, you have to write base case for the size. If you deal with indices, you have to write in terms of indices. So this should have been the case. Ij you do not need, ideally. So okay. Huh? Oh, 1 is equal to R. Okay, let's get rid of this. So this is both are 1 1. Still one more test work. Now you will get TLE. Yes, because this is a dynamic programming problem. It says your recursion tree is becoming bigger and bigger. It's unoptimized solution. You're solving a lot of sub problems, so optimize it. So third test case is for DP. Yeah, yeah. Because in first two test cases, the constraints that we have put, the matrices we are giving you is very small. Third test case, we started giving you bigger matrix. Now let's see the efficiency of your code. And that's where if you do not use DP, it's like Fibonacci problem. If you calculate bigger numbers, Fibonacci numbers, we saw in recursion tree, it was taking longer time. So this is where it is taking longer time. These two test cases are backtracking test cases. Third one is DP test case. So how do we make it DP now? Yeah, then you need a helper also because you have to somewhere initialize that 2D array for every test case separately. Right, so can we convert this into, let's say this was your original, let's make it helper. Let's make it helper. Let's make it helper. And you will make original call to your helper. Let's say return H R comma C, correct? Now here you have a freedom to create a DP matrix. DP is equal to new int. Let's take 100 by 100. I don't know if constraints we have given or not. Then we have to initialize this for int I0, I less than. By default, they will be filled with zeros. Let's not initialize with -1. Let's leverage the value 0. We say if DP of R and C is 0, if it is 0, it is not filled. You can say if it is not 0, else right. In such cases, we should always take it one element additional because now if this is the size for 100 by 100 also we should return this. So let's try to submit this and see. Huh? No, in this problem we are not going Overflow we are not doing. Ideally, if problem statement says that give me answer in modulo, then we go and truncate. In this problem statement we have not called. So now you see with DP, this is working. Sure. The same one?
Sandeep, I have a question.
Yeah.
Yeah, so in the second problem that you just changed to DP, while
Mm-hmm.
setting the question, how do you decide actually which test case would fail if the solution is using backtracking? So
Okay, good
I'm asking
question.
because it would help me, decide the algorithm that needs to be applied looking at the test.
Certainly. Certainly. So mostly these computers that we have, if your time complexity is falling in this range, if you are doing 10 to the power 8 calculations, we are accepting it. Right now, how do you say like this is 10 to the power 8? So think of it. If I say your solution is going to be 2 to the power 50, ideally we know when we make two recursive calls, the time complexity is 2 power n. Do you agree with that?
Yeah.
So I say if I take 50 by 50 matrix and imagine this becomes 2 power 50, then it's 2 power 10 power 5. It's 10 power 3 power 5. See, it becomes 10 power 15. Even if
Yeah.
I give you a 50 plus 50 matrix, I know this is the number of calculations you will do in backtracking. It will not fit here, so you will be gone. Right?
Okay. And how did you come up with the number 10 to power 8?
No, this is a known number. Okay, there is calculation behind that, but for now you can stick to like this is a number that competitive programming sites will accept, will allow. Ideally, this is depending on your CPU's gigahertz. These many calculation our modern day computers are able to do it.
Okay.
To
Got it.
do it in 1 to 3 seconds. So there is some calculation based on processing. So you can keep this in mind. Why I'm saying
Okay.
keep this in mind is imagine if I say there is an array of size 10 to the power 5. If I give
Okay.
you an array of size 10 to the power 5 and I say sort it, if you use insertion sort, looking at the constraints, how many calculations you will be doing? Insertion sort is n square complexity.
10 per 10.
So looking at this constraint, you can tell, hey, insertion sort will not work.
Yes. Got it.
Makes sense? Now,
Yeah.
if I say will n log n pass this constraint,
N would be 10 power 5 and log n would be 5.
10 to the power 5, let's take it 6 itself so that we take a little higher. 10 to the power
Okay.
5 log base 2, 2 to the power 20. 20 into 10 power 5. Will that pass?
Yes.
Yes. So you say, okay, based on constraint, n square solution will not work at all. I have to come up with n log n solution.
Got it. Thanks.
If this is return 1, Savita, what are you doing? You are going from up to down or down to up? Then this is wrong, right? It will not be 1 1. No? When you are coming from here to here, this is your base case, isn't it? And at this case, your I will be, yeah. But I don't see you are going up to down because where are you passing? Wait, this is confusing. If you want to go up to down, you will be writing a separate function, right? R and C are the dimensions. You cannot modify this. Ideally, let me change. If you are going up to down, you need the indices where you are. And I and J you still need. R and C you still need for boundary. Right? So this becomes your helper function. This was your original function. First call that you make is 0 0. Now you see, now you can put a boundary that if R is equal to I minus 1 and J is equal to C minus 1, only then you return. This is your base. Now you can make this call, but R and C you are still passing. This should have been your code. Because when you have only R and C, you cannot go from the other side. Here I have to change it to the calls to helper because this takes 4 parameters. So this was the issue in your code, but this is not still DP. Yeah, boundary case is not there. If boundary, then what do we do? If I is greater than equal to R, there are 0 paths. If we don't put the boundary case, it will keep going out of the boundary and it will keep troubling us. Which one? Max Heapify, sure. Yeah, so this will fail your DP test case. Amit, you are done with 4? Third. First two everyone is done with matrix based questions. Okay, so let's talk about third now. Third question is max Heapify down, right? So what we are doing in max Heapify down, we are given an array and an index. This is the function you are writing. You are writing another function, Heapify down. So when you got this index, this mi is what? This is left child, right? If left child is greater than n, even equal to n is outside, right? Right. Okay, this is one. This is one. If left child is greater, you are directly swapping y. 5 will be swapped with who? Why? Why not 9? If you swap with 6, then right side is a problem, right? So you cannot go ahead with swap until unless you have compared both. Because biggest out of these two should go up. Right? Yeah, Amit, where are you stuck in this? Okay. Yeah, in Heapify down, everyone is clear with the approach. When we are at any index, two things are there. One, do we continue swapping or we stop? We stop if this is highest than these two. That's the stopping point. We don't do anything, right? If left one is higher than this and right, then we swap with left and we continue the same Heapify operation on the left part. If right side is max, you swap with right and you continue, but you will go only one side, either left or right. You will never go both the sides. In your code, you are going both sides. Right? So yeah, it's corrected. Anyone else who is struggling with Heapify down? Because Pranav is saying to take a look. Sure, Pranav, I am opening your code. Yeah. Pranav, this is for, what is this read line doing?
That is just reading the number of inputs, not doing anything. I don't need that variable.
Okay.
So I'm not using it.
Because here you are reading entire line and splitting them, right?
Yeah.
Sure. So you can ignore that, fair. Then you are reading as an int array. Then you are reading that index. And then you are doing Heapify. So that was the syntax. Given index, bad. Okay. Heapify. So Heapify wise, you are taking n as length. Left child is this, right child is this. So you are calculating what is the max index. So now Pranav, think about here. You have changed max here, right?
Yes.
Here you will compare with max or you will compare with IDX? Think of this case. If it is 5, this is 6, this is 9.
Yes, yes. At this very moment, I have to check max again.
Yeah, because you have already updated that out of these two, you know.
Yeah, update. Yeah. Hey, thanks, Anand.
Sure. Shubham, where are you stuck? Sure. So ideally, if you see, the last question will be where you will be implementing complete min heap yourself. You will do insertion, deletion, getting minimum element. So first we mastered only max heapify down. Now here we will be writing up also, down also. So this problem will give you entire practice for min heap. So let's try to wind up at least first 3 questions by 12:30 so that we can spare some time on discussing the concept behind graph. And then if you have any doubts in these questions, we'll take a look.
This conference will now be recorded.
Okay, guys, we are proceeding right now with one more small topic to be introduced to you. And that is related topic to whatever we have discussed so far. Question to you is, what is difference between a tree and a graph?
Graph is a closed structure. Tree is not. Maybe.
Yeah. Graphs can have cycles. Or can we say in tree, between any two nodes, there is only one path. Look at 3 to 4, there is one path. 2 to 6, one path. 2 to 5, one path. So tree is typically said to be undirected acyclic graph. Many times to scare people, some questions are given like, given an undirected acyclic graph, solve this problem. Be aware, this is a tree problem, but it is just the heavy words are used to scare us. Okay. If there is a tree, second condition, one is we say this is undirected acyclic graph. Second thing, we say this is a connected graph. There can be a graph with two nodes, but they are not connected to each other. So 7, 8. Now I can say this entire thing that you are seeing is a graph, even though 7 and 8 are not connected to any other things. Is it possible, like if these nodes are representing countries and imagine there is a sea, ocean between them, you know, the two countries can have connectivity by road, and these countries are connected by road or by rail, but there is an ocean, so they are not connected together. Still, this is a graph. Entire thing is a one graph. Yes. In tree, you will never see that case which is disconnected. So in this case, we say this is a graph with multiple components. We call everything connected together is a component. Right. So this is possible to have a graph like this, but not to have a tree like this. Yeah, when you have multiple trees, what do you call it? In real world, forest. In computers also we call it's a forest. There is a question on forest, right?
We will have something in contest.
Yeah, given a graph, it is forest or not. What it means is you have to guarantee every component of the graph is a tree. Then graph is a forest. Correct? Now the question comes, if this is also a valid graph, how do we represent a graph in memory in computers? Real world applications of graph we already have seen, or we most likely we use every day. What are the real applications of graph? Facebook. Can we say Facebook is a graph or a tree? Let's say this is Amit. Amit is a friend with Rahul. Rahul is a friend with Savita. Savita is a friend with Amit again. It's not a tree. There can be a cycle. So it is a graph. Okay. Social network is a graph. What else? You can say Facebook, LinkedIn is a graph. Google.
Internet. Internet.
Internet. Is internet a graph? Machines are connected to each other. Yes. Google Maps, is that a graph? Cities are connected to each other. We can say that is a graph. Yeah. So these are the real world things that we see that can be modeled as a graph. If we want to model some real world situation as a computer problem, we model that as a graph, and many interview questions are given in such a way that you have to think of that graph yourself. We'll talk that those examples later when we do problem solving on graph. But first is, what is the easiest way for us to come up with a graph notation? In graph, the thing is one node is connected to multiple other nodes. Map. Can we say, if we want to represent a graph,
Adjacency matrix or adjacency list?
Yeah, we'll come to that. Map, what will be the key in map for graph? In map, there is no notion. Okay, anywhere. It can be a node. And what is the value? List of nodes. Adjacent nodes list. So we can say, if we assume all the vertices in a graph are numbered as integers, we can say this is int2, vector of int, or map of integer 2. And if you say this is not a new notation. So ideally, so far you have already dealt with graph problems. It's just that now we are formally introducing it, right? This is one way to represent graph, and this notation also you can call as adjacency list, because you are saying for every vertex I'm storing the list of adjacent vertices, right? Every vertex knows who my adjacent vertices are. This notation is called adjacency list, and this is ever growing because here we are using dynamic lists. You can keep adding more and more nodes to it. If I say to you graph vertices are numbered 1 to n, there are n vertices in the graph, their numbering is 1 to n, that is given to us. Can we use a notation which is less scary than map? Array of what size? N plus 1 size, right? If I say this is an array of size n plus 1 storing what? This is an array of size n plus 1. What does it store? No, in this declaration that you are seeing, how will you describe this line? This is array of size n plus 1, where each location stores an integer. No, not in terms of graph. This stores integer. This is an array of size n plus 1 which is storing. This is an array of size n plus 1 which is storing integer list at every index. So what you are saying is, if I have one dimensional array at index 0, there is a vector. At index 1, there is a vector. So ideally, if you see, I just change the data type. Earlier it was int, I made it vector of int, or I make it a list of integer A, new, I am creating an array, but can I say, if I just simplify it and say data type, this data type can be complex also. Can be int or it can be list. So each array location will represent a list. Ideally, if you see this and this notation has no difference. In map, keys are customizable. Here, keys are fixed from 0 to n-1, but at each location you are storing a integer. Most of the problems that we deal with or that we face in interviews or online coding contests or sites, they typically give one of these two things. Either vertices are numbered from 0 to n-1 or they are numbered from 1 to n. If they are numbered from 1 to n, we take one extra size, we ignore 0 location, we do not even use at all. We say, okay, we will start using from 1 and that's how we deal with this. Clear? Okay. Now, in trees, we talked about.
Can we use a 2D array instead of 1D array?
Yeah, we will come
it
to
will
that.
also serve the purpose, right?
Yeah, we will come to that also.
Okay.
So we have known pre-order traversal in a tree, or in order or post order, and we have done them recursively, right? Or we can also say this was a recursive way of doing things. Right? So if 1, 2, 3, 4, 5. If I say do a pre-order traversal, what will be the output? Pre-order. Print yourself, then go left. In pre-order traversal, what do we do? Print ourselves, go left. Print ourselves, go left. When there is no left, we come back. This is the backtracking step. Go here, print, go left, nothing, go up, nothing, go up. Okay, here also I missed that. This is the pre-order traversal, right? In graph, we say this is depth first search, or call it depth first traversal. We are going in first depth, then coming back next. So when we prepare for exams thoroughly, when we are reading a book, a novel, so book has chapters, chapter have sections, section have content. So in which order do we read the book? When we read from beginning to end, novels especially, we go to first chapter, content of that, every section we complete, then we go look at the next chapter. So we are going depth first, can we say that? And when you are doing revision in last 5 minutes before exam, how do you read that book? We skip through, okay, we say, oh, first chapter, these were the key topics done. Next, these were the key topics done. So ideally we go breadth first, correct? So both ways are there in this. Now the question is, what is difference between DFS and pre-order traversal? Ideally DFS is also pre-order, but when you do it in graph, there is some change that comes. Let me connect 2 to 3. Yeah, so if we have already printed a node, we should not print it again. Duplication is something we want to avoid. In tree, we were never having the duplication concept. Let's try to see now. When you print 1 here, who are the adjacent vertices of 1? 2 and 3. Now it depends how you are storing it in the adjacency list. Let's say 1 is storing its children as 2, 3. 2 is storing as 4, 5. 2 will have 1 also. 2 is connected to 1, 4, 5 and 3. So 1, 4, 5 and 3. 3 is connected to 1 and 2. 4 is connected to 2 and 5. 5 is connected to 2 and 4. So the only thing when we do DFS in graph that we have to avoid is, if we have visited a vertex, we do not want to visit again. That's the only thing we try to make sure. Otherwise, it is totally DFS. Correct? So that is what we will see now. How do we do this DFS? By avoiding duplicates. So what is it that helps us avoid duplicates in a best way? Set. So if you have visited a vertex and you put that in a set, then you can say that I'll not visit again. You will check before visiting it again. Correct? Now let's try to visit that. Starting from 1, you look at all print 1. That is what our pre-order traversal said. Printed 1. Now 1 has the first child as 2. Make a recursive call to 2 and say you do your DFS. Now when we come to 2, we look at the 2's children. 2 has first child as 1. First 2 should print himself. Whenever we make a call to a node, it prints itself. Then it explores all the choices it has. The first choice that 2 has is 1. So what should 2 do with 1? Make a DFS call. It is already visited, but typically we are following a trend that we say whenever recursive call is there, we will make it, let the boundary case handle it. 2 will still make a call to 1. When the call comes to 1, 1 will check, am I visited or not visited? If it is visited, as a boundary it will return back. Correct? So 1 returns back and says, hey, I'm done. So what has happened? 1 went to 2, 2 went to 1, it has backtracked, come here at 2. What is the next choice 2 has? 4. 2 goes and makes a call to 4. Correct? Now when we come to 4, 4 will print himself. What are the choices of 4? 4 had 1. 4 had 1 was there in 4? No, this was 2. 4 has 2. 4 will make a call to 2. 2 will say I am visited. It comes back. 4's next choice is 5. 5 prints himself. With 5 we are doing DFS, right? 5 has a choice of 2 and 4 again. So 5 will also try exploring 2 and 4, but both of them will return back. Correct? So this is how we will keep exploring all the options, keep going back. Ideally, you will realize here also we are doing backtracking only. Correct? So this was the visualization part. Code wise, you will see that it will be very small. If I say we are using, let's say we are using DFS, we are using, what is the notation of graph we use? For now, we stick to using map, let's say vector or list. This is my graph. And when I do traversal, I start with any vertex and I name that vertex as S. Because in graph, when you do traversal, there is no root in the graph. You have to tell with which vertex you have to start. Right? So this is the function that we are talking about. DFS traversal from S. What we talked about, we need additionally to remember who is visited, who is not. Set, or if I say the vertices are numbered 1 to n. Can we use array also of size n or n plus 1? N plus 1, we will take a Boolean array, we will keep marking true and false. So ideally, if you see, set has become a concept now. We can use array, we can use actual set, because we have to just say that it is done or mark it is not done. Right? So we here what we do, we declare a Boolean array and say new Boolean. What should be size of this array? Here there is no n in this function. Map, whatever is the number of keys, plus 1. So we took this array, initialize array as all false, and then we go with the helper approach, DFS helper. In this helper, we give a graph, we give this vertex S, and we also give Boolean array visited. And we will call this function will be like pre-order traversal. We call this function with G, with visited array V, and we say, let's say 0, 1, and visited array V. Let me change this name to V. This is clear? Now help me think about what do we do here. When you land up with S as a vertex, in pre-order traversal, what we used to do? Okay, so you are saying you will print current vertex. So what should we print? What is the current vertex? S. So we will be printing S. Huh? First check Otherwise, we will end up printing again. So we say if S is visited, that's our boundary protecting it. If S is not visited, print S. After printing S, what should we do? Mark it visited also so that it doesn't print again. Correct? Now what should we do? S is printed, S is done. For or children, for C in children of S, what should we do? So if C is not visited, that check we can have here, but we are following, like we'll make a recursive call and let the boundary handle it. So what should we do for every child? G, C, let recursion take care of it. If C is visited, recursion will immediately come back and we will proceed with the next child. Right? One more thing we should do, when we marked it visited, when we are done with it, that I'll let you explore why we are doing this step and why it is needed. This DFS that we did, this is a DFS on entire graph, or this is DFS starting with the vertex. Think of it, if I give you a graph like this, 3, 4, 5. If I start DFS with 1, what will happen? It will print entire graph, or it will print only those vertices that are reachable from this. Only this, right? That means this is not DFS for entire graph. So this is DFS traversal from S. If somebody says do DFS traversal on entire graph, then what we do not get any index or any S here. Then what we do, we take up this array, and since we have to print all the vertices, so what we do, we say if for every vertex I1 less than equal to G dot size I plus plus, do you agree for every vertex I will go and do a DFS? Only if visited of that vertex is false. Yeah, let's say visited we initialize as false. So I say start with 1, do the DFS and keep marking it visited. This will go and do the DFS with 1, it will print 1 and 2. That's over. Now we will not do this step of mark as unvisited, because if once 1 has traversed, if 1 is visited, 2 is visited, both should be marked visited. When we go with 2's DFS, it should be reflecting as visited. We take it here. This is doing DFS with 1 vertex, right? We need that over here also. I'm saying this step now we need to remove, otherwise with 2 also DFS will happen. Is this making sense? Yeah. Let's take 1, 2, 3, 4, 5. We are saying do DFS for entire graph. First we said we will do DFS with 1. If we do DFS with 1, it will print 1 and 2. We want it to mark this visited. So we removed that unvisited step, marking unvisited, so that if one vertex is covered by any DFS, we want it to be covered. Now you think of this loop. When it happened with 1, DFS of 1 proceeded, printed 1 and 2 and marked both of them visited. This DFS will return. Now I will become 2. For 2, visited will be, why false? Here when you are doing DFS of 1, you are marking everything visited and you have never marked them unvisited coming back. So it will remain true. 1 will be visited, 2 will be visited, and they will remain true. So we are tracking this Boolean array at a graph level now. We are not marking them unvisited, right? So 1 is visited, 2 is visited, done. Now for 2, this DFS will not happen again. Do you agree? For 3, what will happen? For 3, visited is false. So you make a call to this DFS function for 3. 3 will print himself and mark it visited. 3 will make call to both the children. Let's say first child is 4. 4's DFS comes, marks it visited. 4 makes a call to 5, marks it visited. 5 doesn't have any unvisited children. 5 returns back to 4, 4 returns back to 3, 3 returns back to main and says I'm done. Now everything got marked visited. This loop will still continue with the next value 4, because this is the for loop for every vertex. Go to 4, 4 is visited, we do not call DFS again. 5, 5 is visited, do not call visited again. So why I'm discussing this is we should know that if somebody says do a DFS on entire graph, we should think in our mind graph can be disconnected also. And if the graph is disconnected, we have to do DFS with every unvisited node so that we don't miss out anything. So this for loop is taking care of every unvisited node once. If we remove this if condition, then what will happen? Good point. Fair. Good point. True. Awesome. Yes. Yes. Will it still work or not if we remove this if condition? Which is fine. We are always going for the simplified code in recursion. And that's why here also we will not putting the check. Ideally here also we could have put the check. If visited of C is false, only then make this call. We could have put that check here also. Right? So your claim is right. Even if we do not put this, it will work. Yes. Because base case will be returned. And that should be fine. If you are using map notation, there will be no duplicates. That has to be guaranteed. Otherwise, your graph itself cannot hold in the map. Okay. DFS, we got it. Same way there is BFS also. That is a lot easier than this. 1, 2, 3, 4, 5, 6. Can we do BFS starting with 1? BFS is like level order traversal. Take 1, put that in the queue first. That is the starting vertex. Also take a visited array, because in BFS also same issue you will encounter. The moment you put 1 in the queue, you mark it visited. So we are making sure queue never gets the same value entering again, right? 1 is visited, done. Then you take 1 out and print. That was our level order traversal. Put first vertex and then go into while queue is not empty, keep looping. Right? 1 will end up putting 2 and 7 in the queue. At the time of putting again, we will check if this vertex is visited, don't put in the queue. Right? If you proceed with that approach, same level order traversal with a visited array will give you BFS. So these two notations, be aware of. Most of the problems, I will say 85% of graph problems are solved with BFS and DFS. That's it. There is third traversal also called topological sort, which we will not go into right now. But DFS and BFS are important and they are correlatable to whatever we have covered so far. Right? Now, let me go back to the skeleton code and think about one thing. Imagine there is a graph given to you, 1, 2, 3, 4, 5, 6, 7. How many components does this graph have? 3. Problem is given a graph, count the components of the graph. How can we count the components? Think of a DFS, the code that we have written. With slight modification, this code can count components. Okay, 2 people are saying what you are saying is right. Let's see, are others able to visualize that? What you said and Sakran you said is right. So we are saying there is a graph with these components. This is the DFS code that we have. What changes do I make to this code and where? Let me bring this condition also back. What changes do we make so that we know how many components are there in the graph? Let's try to visualize our DFS code that was working here. Look at this. First, we are doing DFS with which vertex?
If we find vi equal to false, we can increment the count.
Good. One more person. Yes. So let's say we are doing DFS with 1. What will happen when you do DFS with 1? 1 and 2 will be printed and they will be marked visited also. That means when you do DFS with 1, all the nodes in this component get visited. Can we say that? Will you make a DFS call once again with 2? No. Can we do something in this code so that we know how many components are there? Huh? Every time we are calling DFS, increment the count. So just one change, you say int count is equal to 0. Feel free to ask if you are not yet clear what we are doing. So we said let's take a count. When we did DFS of 1, it covered 2 also. So next time when we come to 2, 2's visited is false. So we don't increment this because 2 is already covered. Any unvisited vertex that we start DFS with, that is counted and we update it. Right? So this will be, we will just modify it to, we'll say return int. Here we will remove the print statement because now we are not printing, just visiting, and here we will end up returning this count. That is the, how do you count? It is said count connected components in a graph. This problem is asked in various ways. There is a college, students are friends with each other. The input of graph is always given like graph has 4 vertices, 5 edges. 1 is friend with 2, 2 is friend with 3, 3 is friend with 4. Like this relationships are given using which we can build a map. And then it says these are the friends. 1 is friend with 2, 2 is with 3. Total there are, let's say there are 11 students in the class and 5 are the connections given to you. And they ask how many gangs are there in the class. Gangs as in, if I am friend with you, you are friend with him, we are part of one gang. We know each other, we are friend with each other. So coding contest sites give you problem like count the gangs in the class when you know who is connected to whom. It's again connected component problem. Using DFS we have solved it. Now think about it, can we solve this problem using BFS also? Breadth first search. Exactly the same thing. It's just that the way we are traversing is different. When you start BFS with one vertex, again it will end up marking all the vertices visited in that, right? So either BFS or DFS solves the problem. Then the challenge is which one we should prefer. Whichever we are comfortable, okay. One is using stack. We know pre-order always uses, this is a recursive, and BFS will not be recursive, it uses queue. The template that we discussed in level order earlier, that's the reason we were emphasizing that let's practice this, because in graph these are the two algorithms that are going to hit us again and again. Right? So ideally we should be comfortable with both by now, and I will say practice both by now because we will see some of the problems where BFS wins over DFS and some problems where DFS wins over BFS. And if we are comfortable with both, then we know 2 ways of solving any graph. Right? One more thought process similar to this. Let's say you have a graph 5, 9, 6, 2, 4. 8. Start with 5. Print all the paths starting with 5, ending at 4. Does it sound familiar, this problem? This is path printing problem. We have done this problem in maps. Start with manager, print path all till ICs. Remember org chart problem. Similar, we have to account for the visited nodes. And when you go back, here you have to mark them unvisited also. So that if 5924 you have visited, you want to print 594 also. That's where when you are going back, you have to mark it unvisited. The DFS step that I was putting, in some cases that will be needed, some cases we will avoid. Right? So this is path printing problem of backtracking only, but now the landscape has changed. If I say from 5 to 4, count how many paths are there. How many paths are there from 5 to 4? Did we do some similar problem today? In matrix, we did path counting problems. From 5, you will make a call to 9, you will make a call to 6. Paths returned by 9, path returned by 6, sum of that is the final answer. Correct? From 5 to 4, give a path where sum of the values in the node is least. Right? So problems are remaining same, data structure is changing, the thought process will remain the same. We'll practice all that when we talk about graphs. Right? One last category which is most famous in graphs is 5, 6, 9, 4, 2, 7. Shortest path from 5 to 2. How do we do that? Shortest path from 5 to 2. Calculate length of all the paths. You make all children calls, minimum of that. Same as min sum path in a 2D matrix that we did. Here also it is done the same. What will that way be? That will be DFS way or BFS way? DFS way. You make first recursive call to the first child, get the answer. Second child, get the answer. Third child, get the answer. Minimum out of that is your final answer. Can we do it BFS way also?
Yes.
Okay. You're saying DFS would be better. Okay. Both are same. If you do BFS way, you remember we talked about level counting. So you take a queue where you are inserting the values and take another queue where you are inserting levels. From 5 is at level 1, 6 and 9 level 2, 4 to 7 level 3. This was level 1, this is level 2, this is level 3. So this is at distance 3, or depends on we are counting vertices or we are counting edges. If vertices we are counting 3, edges we are counting 2. Right? So BFS will also give us the answer. Wherever we reach the destination in the queue, its level is the final answer. Can we say that? Now BFS will give you faster answer or DFS will give you faster answer for this shortest path?
BFS.
DFS. Let's see.
A
This is
breadth first search should give faster answer.
here. Let's say I'm trying to figure out shortest path between 1 and 6. In this case, BFS. Any case where you feel BFS will be slower than DFS?
They are all in one, and from one we are trying to access the last
Mm-hmm.
then DFS will be better.
Okay, BFS is better or DFS is better? We are talking about for finding shortest path. Think about all the cases we challenged. In this case, DFS will be slower than BFS because DFS will first go here. If I add more nodes, I can make your DFS slower. I can think of a test case where 1 to 6, you will take longer time to give the answer. Depends how we are putting them in the adjacency list. I'm saying I can give you an input in such a way that your graph is built this way. Once the adjacency list has 2 first, then 3, then 4, then 5. If I'm giving you that map, right? If I give you a map, there are chances if I make this depth so high that your recursion may use more memory, or it will take longer time. We can do that. But for BFS, can that happen? It traverses this level, then this level. It is guaranteed at third level it will find it. Can we say BFS will reach faster there? Even if it is first node or last node, in adjacency list, wherever it is, we will find it in third step. Can we say that? Yeah, but if nodes are more, it may take longer time. But DFS also will take longer if that is the last node. So BFS typically is preferred when you are doing shortest path problems in undirected graph, because BFS level wise it reaches faster. And this is something we leverage many a times. This BFS approach gives you better solution than even DP. If we do dynamic programming way, we remember the answers, right? If we find overlapping states. There, if we use BFS, many a times BFS beats dynamic programming because it finds the answer faster. Again, it's just a landscape to keep in mind. Yeah. Okay, let's say 5 is leftmost now. Okay. Okay. Correct. Fair. Okay. So in this case, you are saying BFS will take longer because it is going level by level and it will reach 8 in the end. Oh, here it is not there. Correct. That's true. Yeah, this is one particular case where you can say we can tweak the input in such a way that BFS kind of will be worst, right? In this case, DFS will be faster. But in this case, can we say in DFS you would have leveraged the stack already? Imagine even if there was more depth here. Ideally at this level there are less nodes. In queue, you put all the level nodes in the queue, right? Once this level is over, queue will be kind of empty for you. Right? So this depth you will anyways go over. Stack space is what you are losing. Yeah, time you can say they will take same. But BFS will not be bad than DFS. Okay, time wise, because you are saying this is one particular corner case. Yeah, we can say that. Yeah, here I will agree that BFS will be slower. I'll not say slower. Ideally, if we do some results analysis on this, you will see they will be comparable, if not slower, because DFS will have another overhead of calling function, creating stack frames, allocating variables. But yeah, this case, what you have said is perfectly valid. That in this case, DFS will end up traversing all the nodes, and DFS can give the answer faster. But think about it. If you go with the DFS approach in finding the shortest path, will you just say on this basis or you will explore all the paths? No, you are giving shortest path. Now I connected, let's say I connected 7 to 8 also. Will you be able to say based on the first traversal, my answer is this, or you will compare with all the options? If you compare with all the options in DFS, can we say you will traverse all the nodes? Without that, you will not give your answer because all options you would want to explore, right? BFS was also exploring all the nodes and giving the answer in the end. Now, if we compare both, in this case itself, who is better in this case, BFS or DFS? We compare both in terms of time and in terms of space. Time wise, which one is better? Both are equal because both are ending up traversing entire graph. Yes. Space wise, BFS wins. Oh yeah, that's another good catch. In BFS, we will end up saying if from 7 this is there, we can terminate the BFS there. Thanks.
Otherwise, you go to neighborhoods never. BFS wise, you are looking starting from the shortest one. As soon as you find, you are done.
Since you are going level by level, the first time you encounter a node, it is guaranteed that's the shortest path. Can we say that? In BFS, the first time you see the destination node, you say this is the answer. This is the shortest level with which I reached here. Yeah, so BFS will be faster in this case. Yeah. Mm-hmm. I'll start from 6 and check what are all the possible paths. Mm-hmm. And every time I'll go from one path to next node. Where I reach one first, that is my answer. Not even yes. So that way I don't even have to go to all ends and like in BFS you are saying? No, DFS when we say we are making recursive call, exploring all the options, returning the best answer. Like we did finding the minimum value or max sum path in a 2D matrix. You are going right, you are going down, you are getting both these answers and then you are returning your answer. Same point we will reach, but here some path might reach, might not. So yes. Can be reached some So whenever I reach one first, all the paths simultaneously. One whoever I get that path takes as in the assured answer. In this case, okay. So two approaches are there. One level by when you are going. Level by you can say you have assured answer. But if you are not going level wise, you are exploring the first path in depth way, you still have to get the next path and then compare the minimum. So in the previous example that Satyam was giving, if this edge is not there, then they will be equally efficient, you can say, except that recursion call stack. But if this path is there, if there is a shorter path that is existing, then BFS will certainly win over DFS. Right? Either they are comparable or BFS is winning over DFS. We will do problems on that where you can apply both BFS and DFS, and you will see like in shortest path BFS is a preferable way. Yeah, in this example that you gave, remove this red edge, then they are comparable.
In this case, both BFS and DFS are same, like from 9 to 1000.
So there is a graph Savita is giving 5, 6, 7, 8, 9 and up to 1000. And one is connected to all of them. Yeah. And you are finding shortest distance between 1 and 1000. Let's talk about in this case, what will BFS do? You put 1 in the queue, correct? After that, you put level in another queue, level of 1 is 1. Now, when you take 1 out, you will traverse all its children and put them in the queue. When you are putting them in the queue, you encounter, at the time of putting, you say, 1000 is what we were searching for, 1000 is what we got, its level is 2. So we found it at second level. This was first level, this was second level. So in first iteration itself, when you were putting the children, you got it, right? DFS way, if you do, you will go to 1 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 1000. Then you reach there, but then you come back. One said, I have 6 as an option. 6 also we go and say, do you have a shorter path? We come back. We go to 7 also. Now DFS wise, if you see, we are exploring all the paths and seeing that do we find a better answer or not. In this case, BFS will conclude faster and DFS will still explore all the paths because we are not sure that we have left any path. Okay. In Facebook is recommending you friends who are probable friends of, let's say, Satyam. Which algorithm is better to apply? BFS? How we are applying BFS? So we are just recommending mutual friends of a person. So first person, you and your direct friends, that's the data Facebook has, who are probable friends of yours. Friend's friend, that means start a BFS from you, go 2 levels away, and whoever are people there, get their list and say these are probable friends. Now we can apply little more complex logic there. Now the friends list that has come blindly, if we go, 1 has 2, 3, 4, and there is 5, there is 6, there is 7. From 1, this is one level. These are direct friends anyways. 5 and 6, can we say they are probable candidates which we can recommend? Out of 5 and 6, which one will be more preferable? 5. You can also apply that. Give me a friend which is friend with, which is, you are also counting how many paths are there from this to this. You apply these two data, you can come up with your own friend recommendation algorithm. Yeah, if you do DFS here, then you can still, when you do DFS also, you go ahead and get only that level nodes. So pass a level. You remember we used to pass level to left and right. When you are going left or right, keep increasing the level. You can do that way also. Both DFS and BFS will solve the problem. You are terminating DFS here. You are not going beyond that level. So yes, we have to keep. Otherwise, it will be problematic. Otherwise, so graph में निकल जाएगा. Right. So in graph, the critical thing is understanding and learning this BFS and DFS, and then later on thinking how do we apply it to other problems.
So in this case, we
We
are recommending friends to 1 or 3.
are recommending friends to.
1 or 3.
If we are recommending friends to 1 here, then there were 5 and 6.
Most probable one will be 5.
Yeah. Typically, ideally, if we go with the naive approach, we can say 5 and 6 both we will blindly recommend. But out of them also, if you have to rank them, you can see who are more common, having more common friends. Right? Who are the probable recommendations for 3?
5.
Yeah, 4 is not directly connected to 3. 4, 2, 5 is a direct friend, so 2 is getting more value here. Then okay, 6 we will not recommend because 6 is too distance away. Depends on us how many levels we want to go. If you say go to level 3 also, then we get more recommendation, and that's where like these algorithms can be tweaked and we can get more recommendations. Right? Okay. Okay. Idea was to kind of give you a context of DFS and BFS. Coming back to Prakash mentioned one more thing. Prakash said, why are we going with this complex notation? When you say vertices are numbered from 1 to n, I can take a 2D matrix also of size n plus 1 cross n plus 1. These are dimensions of my matrix. And what I can do, 0 row, 0 index I can forget, ignore, because vertices are numbered from 1 to n. If 1 is connected to, let's say 2, if 1 or 2 are friends, I'll put 1. If they are not friends, I'll put 0. If they are friends, if 2 is friend with 1, I'll put 1 here. Otherwise, I can put 0. If 3 and 1 are friends, 1, 1. So we can use matrix also for representing a graph. Right? If you have up to 10 to the power 6 dimensions of matrix, which is, you can say 1000 by 1000 matrix, you can declare easily. Beyond that, if you try to create that big matrix, then it becomes a memory problem. That is one issue with the matrix. Second issue is, in Facebook total, how many users will be there? Billions. And how many friends one person will have? Max 5,000. So if there is a graph where n is, let's say if n is 10 to the power 5, there are 10 to the power 5 vertices in a graph. If you take a matrix, you are taking 10 to the power 5 into 10 to the power 5 size. That first will give you memory limit exceeded, program will not run. Second issue is, even if let's say you are able to create this big memory, most of the rows will end up having zeros in them. It doesn't have this as a friend, this as a friend. Right? So map notation that we talked about, which is adjacency list notation, is more memory efficient. But if you see any graph problem where n is less than equal to 1000, constraints of the problem say this graph is having 1000 vertices, feel free to go with matrix, then you will be dealing with matrix. So for smaller problems, we will stick to using adjacency matrix notation. For bigger lists or bigger graphs, we will use adjacency list. Right? So that is the context of graphs. Summary wise, do we all feel comfortable with backtracking now? Right? If somebody still doesn't feel comfortable with backtracking, graph is going to be hard. So backtracking is the key to reach there. So DFS is dependent on that. Do we feel comfortable in using queue? Now we should also become comfortable in using priority queue. The syntax and basics things we should master, so that when we do new problems, we can apply priority queue there. Some of the problems with priority queue becomes easier to solve. So, and matrices we have seen today. Many matrices problems are given. The key in matrices or array is out of bounds is the most common mistake that we make when we are using matrices. So this is the crux of like whatever we talked about today. Any questions?
Yes. Will we be doing some questions on graph in the
Yes,
upcoming
we will be
lectures?
doing questions on graph. Not today. Today the idea was like introduce it to you. I'm not putting assignments on the graph so far. I'll just put exercises on BFS, DFS which you already have, and this connecting count connected components, so that you can give it a short answer. Not more than these three problems for graph, right? It's so that we utilize this week's time to get familiar with graph notation. There are fixed interview questions on graphs which we will do. Any other questions? Yeah. Okay. Why we were unmarking? Imagine if I say this is a graph. If I say print all the paths from 1 to 5. Right? So when you go from 1 to 5 in this depth way, you would have marked this as visited, this as visited, correct? Now from 1, when you go to, let's say this is also there. So when you go 1 to 2 to 3 to 5, you would have marked all of them visited, right? Now when you go back, now from 1 when you go to 3, 3 will say I am visited. So you will never see 1, 3, 5 path coming. So when we are going back, just unmark them so that next time when you are coming from another direction, you get that. So that was the context of it. Yeah. Any more questions?
So will BFS and DFS be covered again while we are
Yeah.
actually going through the coding of that?
Yes, we will cover
Because
BFS and DFS again.
because frankly speaking, I didn't understand BFS and DFS much today.
Which is fine, Prakash. These problems that we are putting on practice, these are basic BFS and DFS. Give it a try. We anyways will have Wednesday's doubt clearing session. Right, in graph, I'm not adding more problems because this is very important for us to master. So we will cover that. And if you get stuck, ideally you will learn this and understand this when you are trying it yourself. That's the time we are giving to you. This.
Okay.
And if you get any doubts, in the group also. Eight. Okay, so for tomorrow's focus will be, we'll talk DP little more. Today we saw a glimpse of DP, right? So tomorrow we will be doing some more problems on DP where we can come up with recursion, apply DP, and there is a small data structure we will talk about tomorrow. That also we will wind up. No assignments on this. This data structure also has applications, so we should know this. They are helpful in solving a category of problems. And post this week, we will be spending more time on algorithmic thinking. The most frequently asked questions are arrays, strings, and matrices. We'll be sparing more time on those, and we'll be doing a lot of problems where all these concepts that we have learned will keep applying.
Sandeep?
Yeah, Rahul.
Yeah, if you have talked about matrices, right, there is a problem statement called spiral printing of a matrice where we have four for loops inside one master for loop. So
That's
if
right.
you, when you're explaining matrices, just cover that problem statement. I
Yes,
want
yes.
to thinking process of that, like how to approach that problem.
Sure, Rahul. Yeah, we will do more problems on matrices. Today it was just introducing, taking the backtracking. So matrices, arrays, and strings we are going to cover again, and a lot of problems on that.
Sandeep,
Yeah, Shubhi.
for the introduction to graph DFS question, I think there is some error in the input because you have declared in the sample input, you can see the vertex as 8, whereas I think it should be 7. It's going out of bounds for the array.
Just a moment. Here. Yeah,
So
Shubhi.
the nodes should be from 0 to 7, or we have to take v plus 1 as the input size, array size, right?
No, here if you see the vertices are numbered from 0 to vertices minus 1.
Yeah, but in the sample input, the edges are from 8 to 6 as well.
No, should be first line is number of vertices and number of edges. 8 is number of
Yes.
vertices. 8 is the
Yeah,
number of
in the when the edges are declared, you can see 8, 6.
Oh no.
Down, sir. This,
If you see, these are two test cases, Shubhi. This is first test, the second test case.
okay, I think.
This
Okay,
is
I'll
1
check
edge,
again.
2 edge, 3 edge, 4 edge, 5 edge, 6 edge. 6 edge is first graph. Second graph, 6 edges, 8 vertices.
Okay, I'll check the input. I think C# main function input had some out of range exception. I'll check that one.
Oh, okay.
So running till v less than v plus 1.
In this you are saying, if I just submit, you see, like without writing anything, ideally I should get a blank output, right? Okay, this thing you are talking about.
Yeah.
I'll fix it.
Okay.
Yeah, so there is some issue with C# code and the input format. I'll fix that. Okay, any more questions? Anyone?
Exactly. So you have a graph where one is connected to 3.
One is connected to 2.
One is connected to 2.
Okay.
One is also connected to 3.
Okay.
And then 2 is connected to 4 and 5.
2 is connected to 4 and 2 is connected to 5. Okay.
So when you're explaining something, you said that 4, you can reach 4 from 2, 1 and 5. I did not understand that part.
you can reach. What's your question?
You said that 4 column, 2, 1.
Okay.
What is it?
See, when you create a map, 1 is connected to 1 will be the key in the map. What will be the values in the map?
2, 3.
2,
4 and 5.
3 also.
And 1
1
also.
also. Yeah. So this is what? 1, 3, 4, 5. What is 3 connected to?
Okay. 1 and 3.
1 and 2.
Sorry, 1 and 2.
4 is connected to?
4 is connected to only 2. Right?
Only 2.
5 is connected to only 2.
And 5 is connected to only 2. Yes. Yeah. So
You
this
get
is,
not,
or maybe in writing I would have also this. But yeah, now this is the map notation for this graph. And now when we do DFS, we follow this notation and then